Think about the force that holds your feet to the ground, that keeps the moon in its steady orbit around our world, and that guides the majestic dance of galaxies across the cosmos. This same force, gravity, is the silent architect of the universe, a fundamental presence so familiar we almost take it for granted. Yet, for all its everyday influence, gravity harbors secrets that defy our deepest understanding, mysteries so profound that they challenge the very foundations of physics. It is a force that warps the fabric of space and time itself, and today we are setting out on an expedition to confront its most bewildering creations. We are going to explore 30 gravitational wonders that simply should not exist according to our current knowledge, phenomena that range from the curiously small to the cosmically immense, each one a puzzle waiting for its solution. From stars that wink out of existence without any logical explanation to vast cosmic voids where the rules of structure formation seem to have been suspended, the universe is filled with gravitational anomalies that leave even the most brilliant scientists scratching their heads. Why does this matter to you? Because unraveling these cosmic riddles isn't just an academic exercise, it is a journey to the frontier of human knowledge. Each mystery we uncover has the potential to rewrite our textbooks, to reveal a deeper layer of reality, and to answer the most fundamental questions about where we come from and what the universe is truly made of. This is not a dry lecture but a countdown of incredible phenomena, a tour of gravity's greatest hits that will bend your perception of what is possible. So prepare to have your mind stretched and your curiosity ignited. We will venture from the puzzling behavior of spacecraft in our own solar system to the terrifying depths of black holes and the repulsive force of dark energy that governs the ultimate fate of everything. This is a journey into the cosmic unknown, an exploration of the 30 most mysterious gravitational wonders that defy explanation. Each one is a testament to the profound and mysterious power of the force that shapes existence, and together they form a story that is still being written. The adventure begins now. Before we can truly appreciate the strange and baffling anomalies that gravity creates, we need to take a moment to understand the force itself. We all live with gravity every single day. It's the reason a dropped cup shatters on the floor and why we don't simply float off into the sky. For centuries, we understood it much as Isaac Newton did, as an invisible force of attraction between any two objects with mass. This view worked brilliantly for predicting the motions of planets and the path of a baseball. But in the early 20th century, a young physicist named Albert Einstein completely revolutionized this idea. He proposed that gravity isn't really a force that pulls things together in the traditional sense. Instead, he imagined the universe as a four-dimensional fabric called space-time, which combines the three dimensions of space with the single dimension of time. Think of this space-time fabric as a vast, taut rubber sheet. Now, place a heavy object like a star or a planet onto that sheet. The massive object creates a deep dimple, a curvature in the fabric. Smaller objects moving nearby are not being magically pulled. They are simply following the straightest possible path along this curved surface. The Earth orbits the Sun not because the Sun is pulling on it with invisible strings, but because it is rolling around the rim of the Sun's massive dimple in space-time, like a marble spiraling around a funnel. This elegant concept is the heart of Einstein's theory of general relativity. It has proven to be astonishingly accurate, explaining subtle quirks in Mercury's orbit that Newton's gravity could not, and famously predicting that light itself would bend as it passes near a massive object, an effect confirmed during a solar eclipse in 1919. For over 100 years, general relativity has been tested and retested. From the precise timing of signals from GPS satellites to the recent direct detection of gravitational waves, ripples in that very space-time fabric caused by cataclysmic events like colliding black holes. It is one of the most successful and beautiful theories in all of science. Yet, for all its power and precision, this elegant framework begins to show cracks when we push it to its extremes. When we peer into the deepest voids of space or examine the infinitesimally small quantum world, general relativity's predictions sometimes don't match what we actually observe. These discrepancies are not failures, they are thrilling clues, signposts pointing toward a deeper, more complete theory of reality. They hint that our understanding of gravity, as profound as it is, remains incomplete. This sets the stage for our journey into the unknown, beginning with a tiny, persistent mystery that emerged from the silent, dark frontier of our own solar system. Our journey into gravity's greatest mysteries begins not in the distant depths of space, but with two robotic pioneers venturing into the unknown right here in our own cosmic backyard. In the 1970s, humanity was taking its first tentative steps beyond the planets with the Pioneer 10 and Pioneer 11 spacecraft. These intrepid probes had completed their primary missions, providing us with the first close-up views of Jupiter and Saturn, and were now sailing outward on a one-way trip into the interstellar void. As they did, scientists at NASA, our Jet Propulsion Laboratory, were meticulously tracking their positions with incredible precision, using the Doppler shift of their radio signals to measure their velocity down to a fraction of a millimeter per second. And that is when they found the glitch. Despite being so far from the Sun that its gravitational pull was becoming minuscule, both spacecraft were experiencing a tiny, persistent, and completely unexpected deceleration. It was as if an invisible hand was ever so gently applying the brakes, slowing them down by about 10 billionths of a meter per second squared. This may sound immeasurably small, but for physicists calculating trajectories with extreme accuracy, it was a glaring anomaly that refused to go away. For decades, the Pioneer Anomaly was a tantalizing puzzle. Could it be evidence of a flaw in Einstein's theory of general relativity? Perhaps a sign of unseen, non-luminous matter scattered throughout the solar system, exerting an extra gravitational tug? Or was it an indication of something more profound, like a modification to the laws of gravity itself on very large scales? The mystery captivated both professional astronomers and amateur enthusiasts, as it suggested that our most fundamental understanding of physics might need a tweak. The solution, when it finally came, was a masterpiece of scientific detective work that combined painstaking data analysis with a deep understanding of engineering. A team of researchers led by Slava Turyshev dove into decades-old project archives, even recovering data from obsolete 9-track magnetic tapes, to build a supremely accurate thermal model of the Pioneer spacecraft. They realized the answer wasn't coming from outside the probes, but from within. The spacecraft were powered by radioactive plutonium pellets, which generated heat. This heat had to be radiated away into space to keep the instruments from overheating. The team discovered that this radiation was not perfectly symmetrical. A little more heat was being emitted from the back of the spacecraft's main antenna dish than from the front. This anisotropic, or directionally uneven, thermal radiation acted like a very faint but constant photon rocket, pushing gently against the direction of travel and creating the observed minuscule deceleration. It was a subtle engineering effect, not a revolution in physics. While the Pioneer Anomaly is now considered largely solved, its legacy is enormously important. It stands as a powerful reminder that in science, even the tiniest discrepancy between theory and observation can be a portal to a deeper truth. It teaches us the value of meticulousness, of questioning our assumptions, and of looking for clues in the most unexpected places. A patient work to solve this puzzle refined our techniques for navigating deep space and underscored that before we invoke exotic new physics, we must first exhaust every mundane possibility. This lesson in careful observation prepares us for our next wonder, a gravitational quirk that occurs much closer to home, where spacecraft swinging past Earth for a speed boost receive a mysterious and unexplained kick. So if the Pioneer Anomaly was a lesson in solving a mystery through painstaking engineering, our next gravitational puzzle serves as a stark reminder that some enigmas refuse to be so neatly resolved. This one occurs not in the deep, quiet space beyond Pluto, but in the dynamic and bustling region much closer to home during one of spaceflight's most elegant maneuvers, the gravity assist. To send a spacecraft to the outer solar system without an impossibly large rocket, mission planners use planets like cosmic slingshots. A probe like Galileo, destined for Jupiter, or Rosetta, heading for a comet, will swing close by Earth. As it falls into our planet's gravitational well, it steals a tiny fraction of Earth's orbital momentum, whipping around the planet and flinging itself outward with significantly increased speed. It's a beautiful and precisely calculated celestial dance, a testament to our mastery of orbital mechanics, but sometimes the dance has an unscripted step. After several of these Earth flybys, mission controllers noticed something peculiar. When they compared the spacecraft's predicted velocity after the maneuver with its actual, measured velocity, there was a tiny but persistent discrepancy. The change in speed was ever so slightly off, sometimes a few millimeters per second more, sometimes less. This is the Flyby Anomaly. It's as if, during its closest approach, the spacecraft receives a mysterious and unaccounted-for kick, a nudge that our most sophisticated models of Earth's gravity, rotation, and atmosphere simply cannot explain. The effect is minuscule, far smaller than the Pioneer slowdown, but in the world of precision orbital navigation, where a single millimeter per second can compound into a huge targeting error over a journey of billions of miles, it is a significant and troubling glitch. Scientists have put forward a range of hypotheses to explain this oddity. The more conventional explanations point to factors we might not be modeling perfectly. Could it be subtle, unaccounted-for drag from the very outer tendrils of Earth's atmosphere at the altitude of the flyby? Perhaps slight variations in Earth's gravitational field, caused by the uneven distribution of mass in the planet's interior, are playing a role. A more exotic idea involves an effect predicted by general relativity called frame dragging, where a massive rotating body like Earth literally drags the fabric of space-time around with it. This lens-throwing effect is incredibly weak, but maybe, just maybe, it contributes to the anomaly in a way we haven't yet calculated. And then there are the more speculative theories that propose a need to modify our fundamental understanding of dynamics or gravity itself on certain scales. Despite decades of analysis and intense scrutiny, no single explanation has risen to the top as the definitive answer. Part of the challenge is that the anomaly doesn't occur consistently with every single flyby. It seems to depend on the spacecraft's trajectory, its geometry, and other factors we don't fully grasp. This inconsistency makes it even more maddening to pin down. The Flyby Anomaly stands as a humbling counterpoint to the solved case of the Pioneer probes. It shows us that even here, in the gravitational field of our own familiar planet, which we have mapped in exquisite detail, there are still whispers of something we do not understand. It's a ghost in the machine of orbital mechanics, a subtle signature that gravity, even in our own backyard, still holds a few cards close to its chest. This unexpected and unexplained boost during a planetary swing by is a fascinating quirk, but it pales in comparison to the sheer scale of the mystery we encounter when we look to the very edge of our solar system, where the predictable population of icy worlds comes to an abrupt and puzzling halt. After the subtle and perplexing kicks experienced by spacecraft near Earth, we now venture outward, far beyond the orbits of the known planets, to a frontier where our solar system appears to simply end. This brings us to our third gravitational wonder, a mystery carved into the frozen debris at the very edge of our cosmic neighborhood, the Kuiper Cliff. Just past the orbit of Neptune lies a vast, disc-shaped region known as the Kuiper Belt. Think of it as a much larger and more populated version of the asteroid belt, but instead of rocky objects, it is filled with countless icy bodies, remnants from the solar system's formation over 4.5 billion years ago. Pluto is its most famous resident, but it is far from alone. For years, astronomers have been meticulously mapping this distant realm, expecting to find a predictable pattern. The standard model suggested that the number of these icy objects should slowly and steadily decrease the farther out you go from the Sun, tapering off gradually into the emptiness of interstellar space. But the universe, as it often does, had a surprise in store. Instead of a gentle decline, surveys of the Kuiper Belt revealed something startlingly abrupt. At a distance of about 50 astronomical units from the Sun, that's 50 times the distance from Earth to the Sun, the population of these detectable icy objects doesn't just taper off, it plummets. It's as if someone built a sheer gravitational cliff face in space. Beyond this point, the vast reservoir of frozen worlds seems to simply vanish. This dramatic drop-off is far too sharp to be explained by the natural, gradual thinning expected from our models of how the solar system condensed from its primordial cloud of gas and dust. So, what could have created such a stark boundary? What force is powerful enough to sweep this region of space so clean? One of the most compelling and tantalizing explanations points to the gravitational influence of an unseen, massive object. The hypothesis is that a planet, perhaps 5 to 10 times the mass of Earth, could be orbiting the Sun hundreds of astronomical units away. This hypothetical world, often called Planet 9, would have a tremendously elongated orbit that takes thousands of years to complete. As it swings through the outer solar system, its immense gravity would act like a cosmic shepherd. It could gravitationally herd many of the smaller Kuiper Belt objects into clustered orbits with similar tilts, which is another observed anomaly. Simultaneously, its gravitational reach could be clearing out a vast zone beyond the cliff, either by flinging objects into the inner solar system, ejecting them entirely, or preventing them from forming there in the first place. The Kuiper Cliff in this scenario would be the edge of this planet's gravitational domain. However, not every scientist is convinced that a hidden planet is the only answer. Alternative theories suggest that the cliff might be a fossilized relic from the solar system's violent infancy. Perhaps the gravitational pull of a passing star in the Sun's birth cluster, billions of years ago, stripped away the outer material, leaving behind this sharp edge. Or maybe our understanding of how planetesimals, the building blocks of planets, coalesced in the outer solar system, is incomplete, and the cliff represents a natural boundary where the primordial disk of material simply ran out. The mystery is compounded by the immense challenge of observing anything at these distances. Detecting a faint, cold, and slow-moving planet against the blackness of space is like searching for a single specific black marble on a football field at midnight using only a dim flashlight. The Kuiper Cliff stands as a haunting reminder that our exploration of the solar system is far from complete. It is a gravitational fence line in our own backyard, and we have yet to identify the architect who built it. Whether the culprit is a distant, undiscovered world or a flaw in our foundational models, Solving this puzzle will fundamentally reshape our story of how our cosmic home came to be. This concept of a gravitational boundary sculpting the distribution of matter on a local scale is a fascinating prelude to the next level of mystery, where we will see that entire galaxies are governed by similar but far more powerful unseen forces. Moving from the puzzling boundary at the edge of our own solar system, we now cast our gaze outward to the majestic pinwheels of stars that are spiral galaxies. Here, we encounter a gravitational mystery so profound that it forced astronomers to invent an entirely new, invisible component of the universe. This is the galaxy rotation problem, and its discovery began with a simple, logical expectation. When a galaxy spins, you would naturally think that the stars within it behave like the planets in our solar system. The Sun's gravity is strongest close in, so Mercury whips around at a blistering speed, while the outer planets like Neptune and Pluto move at a much more sedate pace. This is a fundamental rule of orbital dynamics. The farther you are from the central mass, the slower your orbital speed should be. Astronomers in the 1970s, like Vera Rubin and Kent Ford, set out to confirm this rule applied to entire galaxies. They meticulously measured the velocities of stars orbiting at different distances from the centers of spiral galaxies, expecting to see those outer stars moving more slowly. What they found, however, sent shockwaves through the world of physics. The data revealed something astonishing and completely counterintuitive. Instead of slowing down, the stars in the outer reaches of these galaxies were orbiting just as fast as the stars closer to the center. The rotation curve, which is a graph plotting orbital speed against distance, was flat. It didn't fall off as expected, it stayed high. This was a monumental discrepancy. According to the combined laws of Newton and Kepler, and based on the gravitational pull of all the visible matter, the billions of stars, the glowing clouds of gas, the dust, those outer stars should not be able to maintain such high speeds. The gravity from the visible mass in the inner part of the galaxy is simply too weak to hold onto them. At the velocities they were traveling, those stars on the edge should have been flung off into the emptiness of intergalactic space, like children spun off a merry-go-round that's moving too fast. The fact that the galaxies weren't flying apart could mean only one thing. There had to be something else there, something we couldn't see. This something else is providing an immense amount of extra gravitational pull, a stronger glue holding the entire galaxy together. The only way to explain the observed high speeds of the outer stars is if the galaxy is embedded within a gigantic, massive sphere of invisible material. This material, which does not emit, absorb, or reflect any light, exerts a gravitational force far beyond that of the luminous stars and gas we can observe. Astronomers named this mysterious substance dark matter. The implications of this discovery are staggering. To make the rotation curves flat, calculations show that this dark matter must outweigh the ordinary, visible matter by a factor of about 5 to 1. This means that everything we can see with our most powerful telescopes, every star, every planet, every nebula accounts for less than 15% of the total matter in the universe. The remaining 85% is this enigmatic, invisible substance that we can only detect through its gravitational handshake. The galaxy rotation problem is arguably the most direct and compelling evidence we have for the existence of dark matter. It's not a subtle effect. It's a glaring anomaly that cannot be explained by simply tweaking our existing models of gravity or matter. While some alternative theories, collectively known as modified Newtonian dynamics or MND, propose that our understanding of gravity itself is incomplete on galactic scales, the dark matter hypothesis has become the cornerstone of our standard model of cosmology. It provides the simplest and most consistent explanation for a wide range of other phenomena, from the way light bends around galaxy clusters to the very formation of the largest structures in the universe. This invisible scaffolding doesn't just keep galaxies from spinning apart, it is the fundamental framework upon which the visible cosmos is built. But if dark matter forms a vast spherical halo around every galaxy, what exactly is the nature of this ghostly, all-pervading substance that shapes the universe yet remains forever hidden from our view? So if the galaxy rotation problem reveals the need for dark matter, the next logical question is, what does this mysterious substance actually look like out there in space? The answer is both elegant and profoundly strange. We now understand that dark matter is not simply sprinkled evenly between the stars. Instead, every single galaxy, including our own Milky Way, is believed to be completely enveloped within an immense spherical cloud of it. Astronomers call this structure a dark matter halo. Picture a familiar spiral galaxy like Andromeda, a brilliant disk of stars, gas, and dust spinning in the void. Now imagine that this entire luminous structure is just the bright, dense core at the center of something much, much larger, extending hundreds of thousands of light years beyond the last visible star, far past the galactic disk, is this gigantic, invisible sphere of dark matter. It's like a firefly trapped at the heart of a vast, transparent crystal ball. The galaxy we see is just the tip of the iceberg. The dark matter halo is the immense, hidden bulk beneath the surface, accounting for the overwhelming majority of the galaxy's total mass. We can't photograph these halos directly, since they don't emit or interact with light in any way we can detect. So how do we know they are there? Their presence is mapped entirely through their gravitational signature. The motion of stars within the galaxy, the orbits of small satellite galaxies around larger ones, and even the way light from distant objects is bent as it passes by, a phenomenon we'll explore later, all point irresistibly to the existence of this massive, extended halo. It is the primary source of gravity that binds the galaxy together. In fact, if you could magically remove the dark matter halo, the entire galaxy would simply fly apart, its stars scattering into the void. The visible matter, the part that makes up everything we know and love, is essentially just along for the ride, tracing out the contours of a gravitational landscape sculpted by this invisible substance. But this leads to one of the most pressing and frustrating questions in all of modern physics. What exactly is dark matter made of? The prevailing theory, and the one that has guided most experiments for decades, is that it consists of a new type of elementary particle that doesn't interact via the electromagnetic or strong nuclear forces. This means it simply passes through ordinary matter and other dark matter particles as if they weren't even there. Scientists have given these hypothetical particles names like WIMP, which stands for Weakly Interacting Massive Particles. Countless experiments are underway deep underground, in abandoned mines and tunnels, trying to catch the incredibly rare moment when one of these particles might bump into an atomic nucleus in a super-sensitive detector. Other experiments, like those at the Large Hadron Collider, are trying to create dark matter particles by smashing ordinary particles together at nearly the speed of light. So far, despite these heroic efforts, we have yet to make a definitive detection. The lack of a direct discovery has kept the door open for alternative ideas. Some physicists propose that our understanding of gravity itself is incomplete. Theories like modified Newtonian dynamics, or MUND, suggest that at very low accelerations, like those experienced by stars on the outskirts of galaxies, gravity behaves differently than Einstein or Newton predicted. In this view, the effects we attribute to dark matter halos might actually be a sign that our fundamental theory needs revision. However, while MUND can explain some galactic rotation curves surprisingly well, it struggles to account for all the gravitational evidence we see, particularly the behavior of massive galaxy clusters colliding with one another. The existence of these vast spherical halos remains the simplest explanation that fits the widest range of observations, even if their fundamental nature eludes us. This ghostly architecture has real, dramatic consequences. The gravitational grip of a large galaxy's dark matter halo is so immense that it dictates the fate of any smaller galaxy that wanders too close. It acts as a cosmic wrecking ball, capable of tearing smaller structures apart through immense tidal forces. The vast, spherical shape of the halo is crucial here. Its gravitational influence is felt in all directions, creating a powerful and inescapable pull that can stretch and distort anything that enters its domain. The aftermath of such a gravitational assault is not a clean disappearance, but rather the creation of a beautiful and haunting cosmic fossil, a visible record of a past destruction that allows us to map the very halo that caused it. The immense dark matter halo that cradles a galaxy is not a passive structure. It is an active participant in a violent cosmic drama that unfolds over billions of years. To witness this, we look to the fate of small, companion galaxies that dare to orbit too close to their gigantic hosts. This brings us to our sixth gravitational wonder, a phenomenon that turns destruction into a thing of haunting beauty: galactic tidal streams. The process begins with a fundamental property of gravity known as a tidal force. This is simply the difference in gravitational pull across an object. You experience a mild version of this every day. The moon's gravity pulls more strongly on the side of the Earth facing it than on the opposite side, leading to the ocean bulges we call high tides. Now imagine that same principle applied on a galactic scale with unimaginably greater power. When a small, dwarf galaxy ventures into the gravitational sphere of a massive spiral galaxy like our Milky Way, it doesn't just get pulled in as a single, cohesive unit. The side of the dwarf galaxy that is closer to the giant feels a much stronger gravitational tug than the side that is farther away. This difference in force, the tidal force, stretches the smaller galaxy. It is literally pulled apart. The process is not a sudden explosion, but a slow, inexorable unraveling that can take hundreds of millions of years. The stars, gas, and dark matter that once constituted the dwarf galaxy are peeled away from each other, no longer bound by their own feeble gravity. They don't simply fall into the larger galaxy and disappear. Instead, they are cast into elongated orbits around the host, following similar paths dictated by gravity. Over eons, these stars become smeared out into vast, faint ribbons that wrap around the giant galaxy like the strands of a cosmic spiderweb. These are the tidal streams. They are the gravitational ghosts of ancient galactic encounters, the shimmering fossils of a long-dead galaxy. The most famous example is the Sagittarius Stream, the remains of a dwarf galaxy that our Milky Way is currently in the process of consuming. From our perspective inside the galaxy, this stream appears as a great arc of faint stars looping around the sky, a celestial river flowing through the darkness. For a long time, these streams were purely theoretical, but with the advent of powerful digital sky surveys like the Sloan Digital Sky Survey, astronomers began to find them everywhere. They are incredibly faint and difficult to detect against the backdrop of billions of other stars, but sophisticated computer algorithms can now pick out these coherent flows of stars, revealing the history of our galaxy as a violent, cannibalistic past. The true power of studying these streams, however, goes beyond simply identifying past victims, because the stars in a tidal stream are moving through the gravitational field of the host galaxy's dark matter halo. Their paths are exquisitely sensitive to the halo's exact shape and density. Think of it like dropping handfuls of glitter into a flowing, invisible river of water. By watching how the glitter moves and spreads, you can map the currents and contours of the river itself, even though you cannot see the water. In exactly the same way, astronomers use the precise positions and velocities of stars within a tidal stream to trace out the gravitational landscape of the dark matter halo. If the halo were a perfect, smooth sphere, the streams would follow predictable paths, but if the streams show kinks, gaps, or unusual densities, it suggests that the dark matter halo is not perfectly smooth. It might have lumps and subhalos, smaller clumps of dark matter within the larger halo, their gravity perturbing the stellar flow. This makes tidal streams one of the most powerful natural laboratories we have for studying the properties of dark matter. The nature of the particle, whether it is cold and clumpy or warm and more diffuse, would leave a distinct imprint on the structure of these streams. By comparing detailed observations with supercomputer simulations, scientists are using these gravitational ghosts not just to reconstruct a history of destruction, but to probe the fundamental nature of the universe's most mysterious substance. The destructive force of gravity has, in this case, created an intricate and delicate tool for discovery. This process of cosmic demolition is a creative force in its own right, but it stands in stark contrast to our next wonder, where gravity seems to have assembled a structure of such perfect and serene symmetry that it challenges our very ideas of how galaxies form. After witnessing the destructive yet creative power of gravity in the grand demolition derby of galactic tides, we now turn our attention to a creation of such serene and perfect symmetry that it seems almost impossible. In the vast and often chaotic tapestry of the cosmos, where galaxies collide and merge in violent embraces, there exists an island of breathtaking order. This is Hoag's object, a galaxy that looks less like a natural structure and more like a piece of celestial art, a cosmic bullseye suspended in the void. Discovered by astronomer Art Hoag in 1950, this object immediately presented a puzzle. Through the telescope, it appears as a nearly perfect ring of brilliant, young blue stars, glowing with intense ultraviolet light, encircling a central core of much older, yellower stars. Between this core and the outer ring lies a wide, dark gap that appears almost completely empty, a deep moat of seemingly starless space. It is a configuration so clean and precise that it defies the messy, hierarchical process we typically associate with galaxy formation. The most intuitive explanation for a ring of stars might be a galactic collision. We know that when a small galaxy punches through the center of a larger disk galaxy, the gravitational disturbance can send waves of density rippling outward, like waves from a stone dropped in a pond. These waves can trigger bursts of star formation in a ring-like pattern, creating what are known as resonance ring galaxies. The classic example is the Cartwheel Galaxy, which shows a brilliant outer ring and a spoke-like structure, clear evidence of a recent violent encounter. But Hoag's object tells a different story. There is no sign of a second galaxy that could have been the impactor, no tidal tails of scattered stars, no distorted debris that would point to a recent collision. The central core is perfectly round and undisturbed, not the elongated bar that often serves as the engine for resonance rings. The gap between the core and the ring is also remarkably clean and wide, unlike the more complex structures seen in collision-formed rings. It stands in majestic isolation, a puzzle that resists the most obvious solution. If not a collision, then how did this perfect circle come to be? One compelling theory suggests that Hoag's object might be an extreme and rare form of a barred spiral galaxy. In this scenario, billions of years ago, it might have possessed a central bar structure made of stars with spiral arms unwinding from its ends. over immense timescales, the bar could have become unstable and dissolved, while the outer arms, rich in gas, continued to orbit. The gravitational dynamics could have then shepherded this gas into a stable, circular ring, where it eventually collapsed to form the brilliant blue stars we see today. The old stars of the former bar and bulge would have settled into the smooth, spherical core. This secular evolution theory is elegant, but it still struggles to fully explain the vast, pristine emptiness of the gap. What gravitational mechanisms could so effectively clear out that entire region, preventing any stars from forming or lingering there? Another, more speculative idea is that Hoag's object is the result of a past accretion event, where it captured a vast cloud of intergalactic gas long after its initial formation. This captured gas, settling into a stable orbit around the existing galaxy, could have then fragmented to create the ring of new stars. However, this also seems unlikely given the sheer quantity of gas required and the precise circular orbit it would need to achieve. The serene beauty of Hoag's object, therefore, masks a deep gravitational mystery. The forces that have sculpted it and that now maintain its perfect equilibrium are not fully understood. It challenges our models by presenting an outcome that seems too perfect, too orderly, for a universe built on randomness and collision. It serves as a reminder that for all the progress we've made, gravity can still assemble structures that leave us in awe and confusion. What makes Hoag's object even more fascinating is that it is not entirely alone. While it is the most famous and perfect example, astronomers have identified other, fainter loop-like galaxies and even some galaxies that appear to have a ring within a ring, suggesting that this phenomenon, while rare, might be a distinct pathway of galactic evolution. Studying these objects gives us a unique laboratory to understand how galactic structures can evolve in relative isolation, driven by their own internal dynamics rather than external violence. The gravitational rules that govern the stability of that starry ring, the balance between the pull of the central core and the orbital motion of the ring itself, are a complex dance that we are still learning to decode. This solitary wonder, a galaxy that seems to have formed in a bubble of cosmic calm, stands in stark contrast to the interconnected forces we explore next, where the motion of our entire galaxy is caught in the pull of a mysterious and immense gravitational anomaly. While galaxies like Hoag's object present mysteries of form and symmetry, our own Milky Way is caught up in a motion of a much grander scale, a journey that involves the entire local cosmos. For a long time, we thought of our galaxy as a relatively isolated island universe, moving through the void with only its immediate gravitational companions for company. But in the latter part of the 20th century, as astronomers began to meticulously map the velocities of galaxies around us, a startling pattern emerged. It became clear that our Milky Way, the Andromeda Galaxy, and all the other galaxies in our local group are not drifting aimlessly. Instead, we are all part of a vast, coherent flow, a cosmic river of galaxies all moving in the same direction at millions of miles per hour. This realization was akin to sitting in a boat on a calm lake and suddenly realizing that your boat, along with every other boat in sight, is being carried along by a powerful, unseen current. The question was, what could possibly be generating a gravitational pull strong enough to dominate the motion of millions of galaxies across such an immense volume of space? The answer, or at least the direction, pointed to a specific region of the sky near the constellation Centaurus. This mysterious gravitational focal point was dubbed the Great Attractor. The name itself evokes a sense of cosmic power and mystery. Imagine a place in space that acts like a gigantic magnet, but one whose force is not magnetism but pure gravity. The Great Attractor is an anomaly of staggering proportions, a concentration of mass so immense that its gravitational influence reigns supreme over a region of space hundreds of millions of light-years across. To exert such a pull, the mass required is almost incomprehensible. It would need to be equivalent to tens of thousands of Milky Way galaxies clustered together. For decades, this posed a profound puzzle. What kind of structure could possibly contain so much mass? The most logical candidate was an unprecedentedly massive supercluster of galaxies, a dense knot in the cosmic web where thousands of galaxies are gravitationally bound together. But there was a major problem, a cosmic obstacle that prevented us from seeing this supposed behemoth directly. The Great Attractor lies in a direction that is almost perfectly obscured by the disk of our own galaxy. This region is known to astronomers as the zone of avoidance. It's not a place of danger, but rather a band of sky that is difficult to observe because it is filled with the gas, dust, and dense starfields of the Milky Way's spiral arms. Trying to see through this zone is like trying to peer through a dense fog bank or a heavily frosted window. The light from distant galaxies is absorbed and scattered by all this intervening material, making them incredibly faint and difficult to detect. For a long time, the zone of avoidance meant that the precise nature of the Great Attractor remained a subject of speculation. Was it a single, monstrously dense cluster? A vast, elongated wall of galaxies, or could it be something even more exotic that our models hadn't predicted? The quest to lift this cosmic veil required moving beyond traditional optical telescopes. Astronomers turned to instruments that could see in wavelengths of light that can penetrate the dust, particularly infrared and radio waves. Pioneering surveys, like those conducted with the Parkes Radio Telescope in Australia, began to painstakingly map the galaxies hidden behind the Milky Way's glare. Slowly, a picture began to emerge. The Great Attractor was not a single, mysterious object, but rather the central gravitational heart of a gigantic supercluster, now known as the Laniakea supercluster. Laniakea, a Hawaiian word meaning immense heaven, is an appropriate name for a structure that contains over 100,000 galaxies, including our own local group. The Great Attractor represents the central gravitational valley of this vast cosmic continent, the point toward which all the galaxies in Laniakea are flowing. However, the story doesn't end there. Our motion toward the Great Attractor is just one part of an even larger and faster flow. It turns out that the entire Laniakea supercluster, with the Great Attractor at its core, is itself being pulled toward something else, an even more massive concentration of mass far beyond it. This reveals a crucial truth about the universe. Gravity operates on every scale. Just as Earth's gravity holds the Moon, and the Sun's gravity holds the planets, and the Milky Way's gravity holds its satellite galaxies, the pull of these immense superclusters dictates the motion of entire galactic families across the cosmos. The Great Attractor, once a total mystery, is now understood as a major landmark in this hierarchy, a powerful gravitational waypoint on our universe's map. But if there is a powerful force pulling us in, the laws of physics suggest there must also be a corresponding region of emptiness, a place with unusually weak gravity that is effectively pushing us away. So we've seen how the immense gravitational pull of the Great Attractor acts as a cosmic anchor, drawing our entire galactic neighborhood toward it. But the story of our motion through the universe has another, equally important side. Think of it not just as being pulled, but also as being pushed. This brings us to our ninth gravitational wonder, a concept that flips our intuition about gravity on its head, the Dipole Repeller. The principle behind it is beautifully simple, yet its implications are profound. In the grand scheme of the cosmos, motion is always relative. Our journey isn't dictated by a single force pulling us from one direction. It's the result of a balance, or more accurately, an imbalance between two different kinds of regions. On one hand, you have areas of extreme density like the Great Attractor, whose powerful gravity acts as a magnet. On the other hand, you have their cosmic opposites, vast, sprawling deserts of space known as voids. The Dipole Repeller is one of these voids, an enormous, underdense region of space located in the opposite direction from the Great Attractor. To understand how a void can push, you need to think about gravity not as an active force that reaches out and grabs things, but as a consequence of the landscape of space-time. Imagine you're on a hill. You naturally roll downhill toward the valley because that's the direction of the steepest slope. Now, picture the universe's large-scale structure as a series of mountains and valleys. The Great Attractor is a deep, massive valley, a gravitational low point. The Dipole Repeller, in contrast, is a vast, flat plateau or even a gentle rise. Because it contains very little matter, its gravitational pull is exceptionally weak. So, while we are certainly rolling downhill toward the Great Attractor's valley, we are also, in a very real sense, rolling away from the high ground of the Dipole Repeller. It's not that the void is exerting a repulsive force. That's not how gravity works. Instead, the gravitational pull from all the matter surrounding the void is stronger than the feeble pull from the void itself. The galaxies and clusters on the far side of the Dipole Repeller are tugging on us more powerfully than the emptiness in between. The net effect is that we are being pushed away from the underdense region and toward the overdense one. It's a cosmic game of tug-of-war where one team is incredibly strong and the other team is almost non-existent. Our motion is the result of this push and pull, technically called a dipole because it has two poles, one of attraction and one of effective repulsion. Pinpointing the Dipole Repeller was a tremendous challenge because, by its very nature, it's a region of nothingness. You can't see it directly. Astronomers had to infer its existence and location by carefully studying the peculiar velocities of thousands of galaxies, essentially mapping the flows and currents of the cosmic ocean to deduce where the deep trenches and empty basins must lie. This discovery fundamentally changed our perspective on the universe's structure. It showed us that the cosmos isn't just defined by the glittering cities of galaxy clusters. It's equally shaped by the immense, dark countryside of the voids. The gravitational landscape is a complex tapestry woven from both dense knots and gaping holes. The interplay between these regions dictates the motion of galaxies on the largest scales, a slow, majestic dance choreographed by the distribution of both visible and dark matter. This cosmic tug-of-war, governed by the gentle but relentless pull of gravity, operates across billions of light-years. Yet, this same force of attraction can, under the most extreme conditions, become so overwhelmingly powerful that it creates a place where the normal rules of physics break down completely, a region of such ultimate density that it represents gravity's final victory. From the immense cosmic currents that push and pull entire superclusters of galaxies, we now venture into a realm where gravity achieves its most absolute and terrifying form. This brings us to a wonder that is not about what gravity does to the motion of objects, but what it does to the very fabric of reality and information itself. We arrive at the black hole information paradox, a puzzle that strikes at the very heart of modern physics and forces a confrontation between our two most powerful descriptions of the universe, Einstein's theory of general relativity and the strange rules of quantum mechanics. To understand the paradox, we first need to appreciate the starkly different pictures these two theories paint of a black hole. Through the lens of general relativity, a black hole is the ultimate victory of gravity. When a massive star collapses under its own weight, it can crush itself down to a point of infinite density called a singularity. This singularity is shrouded by a boundary known as the event horizon, the point of no return. Once anything, a particle, a spaceship, even light, crosses that horizon, it is irretrievably lost to the outside universe. What makes this picture so striking is its beautiful simplicity. The great physicist John Wheeler summarized it with the phrase, "A black hole has no hair." This means that according to Einstein's equations, a black hole can be completely described by just three properties: its mass, its electric charge, and its spin. It doesn't matter whether you form a black hole from a collapsed star made of hydrogen or from a giant ball of old books and furniture. If the resulting black holes have the same mass, charge, and spin, they are absolutely identical. All the intricate, detailed information about what fell in the atomic structure of the star, the words printed on the pages of those books, seems to be utterly erased, lost forever behind the event horizon. This is where quantum mechanics enters the stage and objects violently. Quantum mechanics is the set of laws that governs the behavior of particles on the smallest scales, and one of its most sacred principles is the conservation of information. This principle states that information about the state of a quantum system can never be truly destroyed. It can be scrambled, it can be transformed into an incredibly complex form, but it cannot be erased from the universe. Think of it like burning a book. To your eyes, the information seems gone, reduced to ashes and smoke. But in principle, if you could track every single atom of carbon, every molecule of gas released in the smoke, and measure them with infinite precision, you could theoretically reconstruct the entire book. The information is still there, just hideously difficult to recover. Quantum mechanics insists that this must always be the case. The universe, in a sense, keeps perfect and eternal records. So here lies the paradox. General relativity says that when something falls into a black hole, its information is irretrievably lost, vanished from our universe. Quantum mechanics says that such a loss is fundamentally impossible. Both theories are spectacularly successful in their own domains, but they offer completely contradictory answers to this fundamental question. For decades, physicists assumed that the mighty gravity of the black hole simply overpowered the quantum rule, that the singularity was a place where physics truly broke down and information could be destroyed. This was the accepted view until the 1970s, when Stephen Hawking made a revolutionary discovery. He realized that when you apply quantum theory to the space just outside a black hole's event horizon, a remarkable thing happens. The black hole isn't completely black. It should actually glow with a faint thermal radiation, now famously known as Hawking radiation. This radiation is created when pairs of virtual particles spontaneously pop into existence from the energy of the vacuum, as they do everywhere in space. Normally, these particle-antiparticle pairs annihilate each other almost instantly. But if this happens right at the event horizon, one particle can fall in while the other escapes. The escaped particle becomes real, carrying away a tiny bit of the black hole's energy, which means its mass slowly decreases. To an outside observer, the black hole is evaporating. The problem, however, is that Hawking radiation is purely thermal. It's like the heat radiating from a stove. It contains no specific information about what fueled the fire. So, if a black hole evaporates completely over eons, disappearing in a final burst of particles, what happened to all the information about the stuff that fell in? It seems to have been converted into random, featureless radiation, which is just another way of saying it was destroyed. Hawking's calculation appeared to deepen the paradox, suggesting that information really is lost. This created a crisis in theoretical physics, sparking a debate that continues to this day. The potential resolution to this paradox is one of the most active areas of research, and it likely holds the key to a unified theory of quantum gravity. One leading idea, championed by physicists like Leonard Susskind, is the concept of the holographic principle. This mind-bending proposal suggests that all the information about what falls into a black hole is not lost inside, but is instead encoded in a scrambled, two-dimensional form on the surface of the event horizon, like a cosmic DVD. The three-dimensional interior of the black hole is somehow a projection of this information stored on its two-dimensional boundary. Then, as the black hole evaporates via Hawking radiation, this information is slowly and chaotically leaked back out, imprinted onto the radiation itself. It would be so jumbled that it would be practically impossible to decode, but in principle, the information is preserved. Another fascinating possibility involves the idea of a firewall. If information cannot be lost, then perhaps the event horizon is not the smooth, gentle gateway that general relativity predicts. Maybe it is a seething, violent wall of high-energy particles that instantly incinerates anything that tries to cross it. This would protect the information from falling into the singularity, but it would violate the core principle of general relativity that an observer falling into a black hole should notice nothing special as they cross the horizon. The firewall proposal is controversial, highlighting the deep conflict between the two theories. The black hole information paradox is more than an abstract puzzle, it is a powerful guide. It shows us exactly where our current understanding of physics fails and forces us to invent new concepts that can reconcile the world of the very large with the world of the very small. Solving it would not just tell us what happens to information in a black hole, it would reveal profound truths about the nature of space-time, information, and reality itself. From the profound theoretical paradoxes of black holes, we now turn our attention to a much more immediate and luminous mystery, one that astronomers can actually point their telescopes at and see blazing across interstellar space. Imagine a single object in a distant galaxy, a tiny point of light so energetic that it unleashes more power than a million suns, and it does so not in the gentle light we see, but in the penetrating, high-energy fury of X-rays. These are not the supermassive black holes that lurk at the centers of galaxies, but rather strange, isolated beacons scattered throughout the galactic disks. They are known as ultra-luminous X-ray sources, or ULCs, and their very existence pushes against a fundamental law of physics that has governed our understanding of cosmic power plants for over a century. To appreciate why ULXs are so baffling, we need to understand a concept called the Eddington limit. Think about a star or a black hole that is pulling matter from a companion star. This matter, usually gas, forms a swirling, superheated disk as it spirals inward, like water going down a drain. As this gas is compressed and heated to millions of degrees, it glows brilliantly, emitting intense radiation, including X-rays. However, there is a natural break on this process. The radiation itself exerts an outward pressure. Photons of light, while having no mass, carry momentum, and when they stream outward from the hot gas, they push back against the incoming material. The Eddington limit is the point of balance where this outward radiation pressure exactly equals the inward pull of gravity. It represents the maximum possible brightness an object of a given mass can achieve. If an object tries to shine brighter than this limit, the radiation pressure would become so powerful that it would literally blow away the surrounding gas cloud, cutting off its own fuel supply and causing the brightness to drop. For a typical stellar mass black hole about 10 times the mass of our Sun, this limit is well understood and is equivalent to a luminosity tens of thousands of times that of the Sun. This is where ULXs throw a wrench into the works. These objects are observed to be shining hundreds of times brighter than that established limit for a stellar mass black hole. Some even exceed the luminosity of our entire sun by a factor of 10 million. It's as if you had a car engine that was designed for a maximum speed of 100 miles per hour, but you look over and see it effortlessly cruising at 10,000 miles per hour without exploding. The laws of physics as we know them say this should not be possible. So, what is going on? Astronomers have been grappling with this question for decades, and two primary explanations have emerged, each with fascinating implications. The first and most straightforward idea is that ULXs are not stellar mass black holes at all, but rather a long-sought missing link in the black hole family, intermediate mass black holes. We are familiar with stellar mass black holes, the remnants of giant stars, and we know about the supermassive monsters at the centers of galaxies, weighing millions or billions of solar masses. But what about the ones in between? If a ULX is powered by a black hole that is 1,000 or even 10,000 times the mass of the Sun, its higher gravity would mean a much higher Eddington limit. It could then accrete matter and shine with the incredible brilliance we observe without breaking the rules. Finding such objects would be a major discovery, filling a crucial gap in our understanding of how black holes form and grow, potentially serving as the seeds for the supermassive ones. The challenge is that intermediate mass black holes are notoriously difficult to confirm, as they are smaller and darker than their supermassive cousins. The second explanation is even more intriguing. What if ULXs are standard stellar mass black holes, but they have found a clever way to cheat the Eddington limit? This would require some exotic astrophysical gymnastics. One possibility is that the emission is not symmetrical. Instead of radiating energy equally in all directions, like a bare light bulb, the X-rays might be funneled into tight, focused beams, much like a cosmic lighthouse. If this beam happens to be pointed directly at Earth, the source would appear far brighter to us than it truly is across all directions. In this scenario, we are not seeing a violation of physics, but rather a cosmic illusion of perspective. Another fascinating cheat code involves the nature of the accretion disk itself. Perhaps under certain conditions, the disk can become incredibly thick and dense, changing how the radiation escapes and effectively allowing more material to fall in without being blown away. Some theories even suggest that the intense magnetic fields around the black hole could play a role in confining the accretion flow, forcing it to behave in ways that defy the simple spherical model the Eddington limit assumes. The truth is, both explanations might be correct, but for different ULXs. The universe has a habit of not being simple. In recent years, observations with advanced telescopes like NAS, a new star, and Chandra X-ray Observatory have provided compelling evidence for the stellar mass black hole with a trick scenario in several cases. For example, one famous ULX named M82X1 has shown pulsations, a regular flickering that is the telltale signature of a rapidly spinning neutron star, not a black hole. This revealed that some ULXs are actually neutron stars with immensely strong magnetic fields, trillions of times more powerful than Earth's. These magnetars can channel the infalling gas onto their magnetic poles, creating incredibly hot, focused X-ray spots that allow them to supersede their Eddington limit. This discovery added a whole new layer of complexity, showing that ULXs are not a single class of object but a phenomenon that can be produced by different kinds of cosmic engines using different physical loopholes. Ultra-luminous X-ray sources, therefore, are more than just bright spots in the sky. They are extreme laboratories where matter is subjected to gravitational forces and magnetic fields of almost unimaginable power. By studying them, we are not only hunting for missing links in the black hole family tree, but also stress-testing our fundamental theories of how gravity and radiation interact in the most violent environments imaginable. They challenge us to think beyond textbook simplifications and consider the complex, dynamic, and often beamed reality of cosmic accretion. The incredible power generated by these solitary objects, whether through sheer mass or clever physics, is a testament to gravity's ability to create the universe's most powerful engines. But sometimes the most extreme gravitational environments are not forged by a single object, but by the deadly dance of two. After exploring the solitary brilliance of ultra-luminous X-ray sources, we now turn to a far more violent and collaborative spectacle, one where two of the universe's most extreme objects come together in a cataclysmic finale. This is the mystery of the black hole-neutron star merger, a cosmic event of almost unimaginable ferocity. Picture the scene: a black hole, an insatiable gravitational pit, and a neutron star, the incredibly dense crystalline corpse of a giant star, locked in a mutual orbit. This is not a stable arrangement. With each passing orbit, they lose energy in the form of gravitational waves, spiraling closer and closer in a dance that can only end in total destruction. The neutron star, a sphere of pure nuclear matter so dense that a single sugar cube-sized piece would weigh billions of tons on Earth, is about to meet a force that can crush even it out of existence. The central question of this mystery revolves around the final moments of this fatal embrace. As the neutron star approaches the black hole's event horizon, it experiences an extreme difference in gravitational pull across its diameter. This tidal force is the same principle that causes ocean tides on Earth, but amplified to an astronomical degree. The key unknown is the mass ratio between the two objects. If the black hole is relatively small, only a few times the mass of the neutron star, its event horizon is also small. In this scenario, the tidal forces become overwhelmingly powerful, while the neutron star is still a significant distance away from the point of no return. The black hole's gravity would then stretch and shred the neutron star, tearing it apart into a spectacular, elongated stream of ultra-dense matter that wraps around the black hole before ultimately being consumed. This process, happening just outside the event horizon, would be a cosmic blender of nuclear material, creating intense conditions for a brief, fiery display. This is where the potential for a multi-messenger astronomical event arises. The act of tearing the neutron star apart and flinging its debris into a hot, swirling accretion disk around the black hole could unleash a tremendous burst of energy across the electromagnetic spectrum. Astronomers hope to see a kilonova, a flash of light similar to the one produced when two neutron stars merge, which forges heavy elements like gold and platinum. The difference here is that the presence of the black hole adds a terrifying new variable. The timing and intensity of the light would depend critically on the black hole's mass and spin. A rapidly spinning black hole could allow the neutron star to venture closer before being disrupted, potentially leading to a brighter and more prolonged emission. The detection of such a flash of light, coordinated with the distinctive chirp of gravitational waves signaling the merger, would be a scientific bonanza, offering a direct window into the physics at play. However, there is another, more somber possibility. If the black hole is very large with a mass tens of times greater than the neutron star, its event horizon is correspondingly vast. In this case, the tidal forces might not become strong enough to rip the neutron star apart until it has already crossed the event horizon. From the perspective of the outside universe, the neutron star would simply vanish, swallowed whole without a trace. It would be a quiet, dark merger, emitting a clean gravitational wave signal but no accompanying light show. The neutron star would be gone, leaving behind only a slightly more massive and perhaps slightly perturbed black hole. Determining which of these scenarios occurs more frequently in the universe is a primary goal of observatories like LIGO and Virgo. Each gravitational wave signal from such a merger carries subtle fingerprints. The masses, the spins, the precise shape of the chirp that can tell us whether the neutron star was tidally disrupted or swallowed intact. The importance of solving this mystery extends far beyond the drama of the collision itself. Neutron stars are natural laboratories for matter at nuclear density, a state impossible to recreate on Earth. By observing how they are torn apart, we can learn about the fundamental properties of nuclear matter, its equation of state which governs how stiff or soft it is. A softer star would be torn apart more easily and at a greater distance from the black hole, while a harder one would resist disruption longer. Furthermore, these extreme mergers serve as the ultimate testing ground for general relativity. The intense, dynamical gravity in the final moments of the inspiral could reveal subtle deviations from Einstein's predictions, potentially offering clues to a more complete theory of gravity. The black hole-neutron star merger is therefore a unique cosmic experiment, one that probes the limits of matter, energy, and spacetime itself. While these collisions represent gravity's most destructive potential, the same force is also responsible for creating objects of such incredible stability and precision that they can be used as the universe's most reliable timekeepers. From the cataclysmic violence of black holes tearing neutron stars apart, we now shift to a realm of almost supernatural precision, where the aftermath of such stellar deaths gives us a tool of unparalleled accuracy. The universe's most reliable timekeepers are not man-made devices, but the spinning corpses of massive stars, pulsars. When a giant star goes supernova, its core can collapse into a neutron star, a city-sized sphere so dense that a single teaspoon of it would weigh 1 billion tons. Some of these neutron stars become pulsars, and if their rotation is aligned just right, they sweep beams of radiation across space like a cosmic lighthouse. As they spin, sometimes hundreds of times per second, these beams flash past Earth with a regularity that rivals and often surpasses the most advanced atomic clocks we can build. This metronomic ticking, stable over decades, provides a foundation for one of the most ambitious experiments in all of astronomy. This incredible reliability is the key to a revolutionary technique known as a pulsar timing array. Instead of building a single, gigantic detector on Earth like LIGO, astronomers are turning the entire galaxy into an observatory. They carefully monitor the faint radio pulses from a network of these cosmic lighthouses, distributed across thousands of light-years. The goal is to detect not the loud, transient chirps from stellar mass black hole mergers, but something far more subtle and pervasive: the steady, low-frequency hum of gravitational waves generated by the most massive objects in the universe. The concept is breathtaking in its scale and simplicity, as these ripples in spacetime predicted by Einstein wash through the galaxy. They do something remarkable. They very slightly stretch and compress the fabric of space itself over astronomical distances. Imagine the space between us and a distant pulsar as a calm, quiet pond. The regular pulse of the lighthouse is like a steady drip of water into that pond, creating ripples that we can time with perfect accuracy. Now imagine a gentle, persistent wave, a gravitational wave from a distant cosmic event passing through that pond. It will ever so minutely alter the distance the pulsar's signal has to travel. When the wave stretches space, the journey takes a fraction of a nanosecond longer. When it compresses space, the journey is a tiny bit shorter. This causes the pulsar's incredibly regular tick to arrive at our telescopes either slightly early or slightly late. The deviation is infinitesimal, perhaps only a few hundred nanoseconds over years of observation, and for a single pulsar, it would be impossible to distinguish from ordinary noise. This is where the array, the network, becomes everything. A passing gravitational wave will affect the timing of pulsars in a specific, correlated pattern across the sky. Pulsars in one part of the sky will have their signals delayed in unison, while pulsars in a perpendicular direction will be affected in the opposite way. By meticulously comparing the timing residuals from dozens of these millisecond pulsars over many years, scientists can search for this distinctive fingerprint. It's like listening to a chorus of perfect clocks and detecting a faint, synchronized waver in their collective rhythm, a whisper-thin signature etched into the fabric of space-time itself. The primary source of this background hum is thought to be the combined signal from countless pairs of supermassive black holes, each weighing billions of suns, orbiting each other in the cores of distant galaxies. These behemoths, on their long, slow spiral toward an eventual merger, generate gravitational waves with wavelengths so long spanning light-years, and frequencies so low that they can only be detected by a galaxy-sized instrument like a pulsar timing array. The first tantalizing hints of this background hum have recently been reported by collaborations across the globe, including the North American Nanohertz Observatory for Gravitational Waves, or NanoGrav, and similar teams in Europe and Australia. After analyzing over 15 years of data, they are seeing a common, low-frequency signal affecting all the pulsars in their array, a noise that swells with a characteristic pattern. While not yet a definitive detection of individual sources, this signal has the hallmarks of the long-predicted gravitational wave background. It is the sound of the universe's heaviest objects dancing a slow-motion waltz, a collective vibration that has been ringing through the cosmos for billions of years. This emerging field is opening an entirely new window on the universe, allowing us to listen to the gravitational symphony of supermassive black hole binaries, to census their populations, and to understand the merger history of galaxies across cosmic time. The steady, patient ticking of these dead stars is giving us a way to hear the deepest, most fundamental rhythms of the cosmos. The steady, patient hum detected by pulsar timing arrays is the collective sigh of the universe's most massive black holes, but to hear the individual cry of a single, catastrophic collision is an experience of a different order entirely. This brings us to one of the most dramatic confirmations of Einstein's genius and a wonder that we can literally listen to, the chirp of a black hole merger. For a century, gravitational waves were a purely theoretical concept, a necessary consequence of general relativity that seemed almost too faint to ever detect. Einstein himself doubted we would ever have the technology to observe these ripples in the fabric of spacetime. But on September 14, 2015, the twin detectors of the Laser Interferometer Gravitational Wave Observatory, or LIGO, heard something that would change astronomy forever. It was not a sight, but a sound, a brief, cosmic whisper that lasted less than half a second. The signal was so clean and so perfectly matched the predictions of supercomputer simulations that it left no room for doubt. After a journey of 1 billion years across the universe, the sound of two black holes colliding had finally reached Earth. The character of this sound is what gives this wonder its name, the chirp. Imagine the sound a small bird makes, a quick upward sweep in pitch that ends abruptly. Now amplify that concept to a scale of cosmic violence. The chirp begins as a very low-frequency rumble, almost imperceptible. This corresponds to the black holes, each roughly 30 times the mass of our Sun, orbiting each other in a slow, stately dance. But as they circle, they lose energy by radiating gravitational waves, causing them to spiral inward ever faster. This is the essence of the chirp, the frequency, and the amplitude, or volume, of the waves increase rapidly as the black holes get closer and whirl around each other at a significant fraction of the speed of light. In that final tenth of a second, their orbital speed becomes a blur, and the pitch of the chirp sweeps upward through the range of human hearing before culminating in a final, sharp peak. This peak is the moment of merger when the two singularities become one, but the story does not end there. The newly formed single black hole is not born calmly. It is a misshapen, wobbling object, ringing like a struck bell as it settles down into a perfect, smooth sphere, as dictated by its final mass and spin. This brief period is called the ring down. The signal doesn't just stop, it reverberates and fades away, carrying information about the final state of the black hole. The entire chirp, from the initial in-spiral to the merger and the ring down, is a data-rich fingerprint. By analyzing its precise shape, physicists can extract astonishing details. They can calculate the masses of the two original black holes, determine how fast they were spinning, and even estimate the distance to the event, all from a faint wobble in a laser beam measured to within a fraction of the width of a proton. The scientific implications of this are monumental. First and foremost, it was a direct and stunning confirmation of a key prediction of general relativity, proving that space-time itself is dynamic and can be warped by accelerating masses. But perhaps even more exciting was the surprise hidden within that first chirp. The black holes involved were about 30 solar masses, which was larger than many astrophysicists had expected for black holes formed from stellar collapse. This hinted at a previously hidden population of black holes, opening up a new field of population studies. We are no longer limited to observing the universe with light. We can now listen to it, and what we are hearing is a universe filled with dark, massive objects constantly colliding. The energy released in such an event is almost beyond comprehension. For that brief moment, the merger of those two black holes radiated more power in gravitational waves than all the stars in the observable universe combined put out in light. It is the most energetic event known to occur since the Big Bang itself, a silent thunderclap echoing through the structure of reality. For nearly 70 years, the central narrative of cosmology was one of a cosmic slowdown. Ever since Edwin Hubble's groundbreaking work in the 1920s revealed that the universe was expanding, scientists had assumed that this expansion must be decelerating. The logic was straightforward and seemed unassailable. Gravity is an attractive force. Every galaxy attracts every other galaxy. Over time, the collective gravitational pull of all the matter in the universe should act as a brake, gradually slowing the expansion that began with the Big Bang. The only real question was how much it was slowing down. Would there be enough matter for gravity to eventually halt the expansion and pull everything back together in a big crunch? Or would the universe just keep expanding forever, albeit at an ever-slowing pace, coasting toward a cold and dark future? This was the great cosmological debate of the 20th century. To settle it, two independent teams of astronomers set out in the late 1990s to make the most precise measurement of the universe's deceleration ever attempted. They aimed to do this by observing a special kind of stellar explosion known as a Type I, a supernova. These supernovae are crucial because they are what astronomers call standard candles. A Type I, a supernova, occurs in a binary star system where a dense white dwarf star steals material from its companion. When the white dwarf reaches a very specific critical mass, it undergoes a runaway thermonuclear explosion. Because this critical mass is always the same, the intrinsic brightness or luminosity of these explosions is also always nearly identical. This makes them perfect for measuring cosmic distances. By comparing how bright the supernova appears from Earth to how bright we know it actually is, astronomers can calculate its distance with remarkable accuracy. Furthermore, by analyzing the redshift of the supernovas, light how much the expansion of the universe has stretched its wavelength, they can determine how much the universe has expanded since the star exploded. By looking at extremely distant supernova which exploded billions of years ago, the teams were effectively looking back in time, mapping out the expansion history of the universe. The results, announced almost simultaneously in 1998, sent a shockwave through the scientific community that is still reverberating today. Both teams expected to find that the more distant supernova, representing a younger universe, were receding from us faster than the models predicted, indicating that the expansion was slower in the past and had been slowing down since. Instead, they found the exact opposite. The distant supernova were fainter than they should have been, meaning they were farther away than expected. The only possible explanation was that the expansion of the universe was not slowing down at all. It was speeding up. The universe's expansion is accelerating. This was akin to tossing a ball into the air, and instead of watching it slow down and fall back to Earth, you see it fly away faster and faster into the sky, defying gravity itself. The discovery was so bizarre and counterintuitive that the team spent years checking and rechecking their data for errors, from potential intergalactic dust dimming the starlight to unknown quirks in the supernova themselves. But the evidence held firm. The universe is accelerating, and for this to happen, there must be something working against the relentless pull of gravity. This mysterious something was given a name that reflects our profound ignorance about its true nature: dark energy. Whatever it is, dark energy appears to be a kind of anti-gravity, a pervasive pressure or repulsive force that is inherent to the fabric of space itself. Its effect is negligible on small scales, like within our solar system or even our galaxy, where gravity reigns supreme. But on the very largest scales, across billions of light years, the cumulative effect of dark energy becomes dominant, overwhelming the gravitational attraction of all the matter, both visible and dark, and pushing the universe apart at an ever-increasing rate. The most mind-bending aspect of this discovery is its implication for the composition of the universe. Measurements now indicate that dark energy constitutes about 68% of the total energy content of the cosmos. Dark matter makes up about 27%, and all the ordinary matter that makes up stars, planets, and us accounts for a mere 5%. We are living in a universe dominated by two invisible components we do not understand. So what could dark energy possibly be? The leading candidate is the simplest one, at least mathematically: Albert Einstein's cosmological constant. Back in 1917, when Einstein was applying his new theory of general relativity to the universe as a whole, he found that his equations naturally described a universe that was either expanding or contracting. This bothered him, as the prevailing view at the time was of a static, eternal universe. To force his equations to describe a static cosmos, he introduced a fudge factor, a term represented by the Greek letter lambda, which represented a repulsive force that would perfectly balance the attractive force of gravity on large scales. When Hubble later discovered the expansion, Einstein famously called the cosmological constant his greatest blunder, and it was discarded for decades. Now it has made a spectacular comeback. In this view, dark energy is simply the energy inherent to the vacuum of empty space itself. According to quantum physics, empty space is not truly empty. It is a seething foam of virtual particles constantly popping in and out of existence. This quantum vacuum should have an energy associated with it, and this energy would produce a repulsive gravitational effect, exactly like the cosmological constant. The problem, however, is one of the most infamous discrepancies in all of science. When physicists try to calculate how strong this vacuum energy should be based on quantum theory, they get a number that is about 120 orders of magnitude. That's a 1 followed by 120 zeros, too large. If the cosmological constant were that strong, the universe would have been torn apart before galaxies could even form. So why is the observed value of dark energy so infinitesimally small, but not zero? This is the cosmological constant problem, and it remains utterly unresolved. The other major possibility is that dark energy is not a constant at all. Perhaps it is a dynamic field that permeates space, similar to the Higgs field, but with repulsive gravitational properties. Theorists have given these hypothetical fields names like quintessence, a term borrowed from ancient Greek philosophy meaning the fifth element. A quintessence field could change in density and strength over time. It might have been weaker in the past and could grow stronger or weaker in the future. This would mean the acceleration of the universe is not a permanent feature but could potentially reverse. The fate of the cosmos would then hang in the balance of a competition between dark energy and gravity that could change over billions of years. Current observations, including precise measurements of the cosmic microwave background, strongly favor the simple cosmological constant model, but the door is still open for more complex dynamic theories. The ultimate nature of dark energy remains one of the most profound mysteries in physics, and its resolution will determine the final fate of everything. If the acceleration continues indefinitely, as a cosmological constant suggests, the universe faces a cold and lonely future known as the Big Freeze or heat death. Galaxies beyond our local group will eventually be pushed away so fast that their light will never reach us, leaving the sky dark and empty for any future civilization. The cosmos will become an ever-expanding, increasingly isolated, and frigidly cold void. This repulsive force, the greatest mystery in cosmology, not only dictates the ultimate fate of the universe, but also plays a crucial role in sculpting its largest structures, creating the vast, empty deserts we call cosmic voids. After exploring the immense, ghostly halos of dark matter that sculpt entire galaxies, we encounter a phenomenon that represents the exact opposite, a staggering, almost unimaginable emptiness. If dark matter is the unseen substance that clumps the universe together, then cosmic voids are the vast, empty spaces in between, and the king of these voids, the most famous and profoundly empty region we have ever discovered, is the Boötes Void. To call it a void is an understatement. It is a cosmic chasm of nothingness so vast that it defies easy comprehension. Imagine a sphere of space so large that it would take a beam of light, traveling at the universe's ultimate speed limit, over 330 million years to go from one side to the other. Now imagine that within this colossal volume there are almost no galaxies. When it was first discovered in the 1980s, astronomers found only a handful of galaxies where their models predicted there should be thousands. It is a gravitational desert on a scale that is difficult to grasp, a place where the universe's usual rules of structure formation appear to have been suspended. The existence of such a void poses a direct challenge to our best models of how the cosmos evolved. According to the prevailing Big Bang theory with inflation, the universe started in an incredibly hot, dense state and then expanded rapidly. Tiny quantum fluctuations in this primordial soup were stretched to enormous sizes by inflation, creating slight variations in density. Over billions of years, gravity got to work on these seeds. The slightly denser regions pulled in more and more matter, eventually growing into the galaxy's clusters and the great cosmic web we see today. The less dense regions, in turn, were drained of their material, becoming the voids. This is a process we understand, but the Boötes Void is different. It is not just a low-density region, it is an extreme outlier. Its sheer size and profound emptiness suggest that either the initial seed for this void was an improbably large underdensity, or something unusual happened during or after its formation to make it so empty. Gravity, which acts to pull matter together, should have worked over the eons to slowly fill this void with material from the surrounding filaments. The fact that it remains so empty is a puzzle. It's as if a large city were built with a perfectly circular, vacant lot in the center spanning hundreds of blocks, a lot that has somehow resisted any and all development for the entire history of the city. Scientists have proposed several ideas to explain this great nothingness. The simplest explanation is that it is just a statistical fluke. In any random distribution, no matter how uniform, you can occasionally get a very large gap just by pure chance. Think of it like rolling dice. If you roll a die 6 times, you might not get a single 6. That's not surprising. But if you roll it 1,000 times and never get a 6, you'd start to suspect the die is loaded. The Boötes Void might be the cosmic equivalent of an incredibly unlikely, but still possible, run of bad luck in the distribution of matter. The universe is so vast that even the most improbable events are bound to happen somewhere. In this view, the void isn't a crisis for cosmology. It's just a fascinating example of cosmic variance, a reminder that the universe is not perfectly smooth. However, its sheer scale makes the statistical fluke explanation feel a bit unsatisfying to some. This has led to more exotic theories. Could the void be evidence of a past catastrophic event? One speculative idea involves the hypothetical concept of cosmic strings. These would be unimaginably thin, incredibly dense defects in the fabric of spacetime, relics from the very early universe possessing immense gravitational fields. If one of these strings had passed through the region that became the Boötes Void, its gravitational influence could have literally pushed matter away, clearing out a vast volume of space. Another, even more speculative possibility involves an ancient collision between our universe and a bubble of a different universe in the multiverse landscape, a collision that might have swept the region clean. While these ideas are fascinating, they remain highly speculative, as there is no direct evidence for cosmic strings or other universes. The Boötes Void, therefore, stands as a monument to our ignorance. It is a quiet, dark corner of the cosmos that challenges us to refine our theories of structure formation. Its emptiness is not passive. It is an active participant in the dynamics of the universe. The galaxies that do border the void are likely being influenced by its lack of gravity, perhaps flowing away from the emptiness and toward the denser surrounding structures. Studying this great void helps us understand not just the empty spaces, but how the full spaces came to be. But if the Boötes Void represents a mystery of emptiness on a grand scale, the next gravitational wonder we encounter strikes at the very heart of our measurement of the cosmos itself. It's a puzzle that isn't about what's in the universe, but about the fundamental rate at which the universe is growing. This is the Hubble Tension, and it has created a crisis in modern cosmology that is both profound and deeply unsettling. For nearly a century, astronomers have been trying to pin down a single, crucial number, the Hubble constant. This number, denoted as h0, represents the current expansion rate of the universe. It tells us how fast, at this very moment, a galaxy 1 million parsecs away from us is receding due to the cosmic expansion. Knowing this value accurately is like having the master key to the universe's history. It allows us to calculate the age of the cosmos, to understand its past evolution, and to predict its ultimate fate. It should be one of the most well-established numbers in all of science, yet it is not. In fact, it has become the source of one of the biggest disagreements in astronomy. The root of the tension lies in the fact that we have two primary and seemingly impeccable methods for measuring this expansion rate. The first method is often called the distance ladder approach, and it focuses on the local modern universe. It's a cosmic ladder with three key rungs. The first rung involves incredibly precise parallax measurements from the Gaia spacecraft to calibrate the distances to nearby stars. The second rung uses a special class of stars known as Cepheid variables. These stars pulse with a regularity that is directly tied to their true brightness. By measuring their pulse rate from the ground and their apparent brightness from space with the Hubble Space Telescope, astronomers can calculate their distance with high confidence. These Cepheids are then used to calibrate the third and most powerful rung of the ladder, Type Ia supernova. As we discussed earlier, these supernovae are standard candles exploding with a known peak brightness. By observing these supernovae in galaxies whose distances have been calibrated by Cepheids, and then looking at much more distant supernova, astronomers can measure the expansion rate directly. This local method is like using a well-calibrated radar gun to measure the speed of cars leaving a city. It gives you a direct, modern snapshot of the expansion. The second method takes a completely different approach. Instead of looking at the local universe, it peers back to the very beginning, to a time when the universe was only about 380,000 years old. This is the era of the cosmic microwave background, or CMB, the afterglow of the Big Bang. This faint radiation which fills the entire sky is a perfect snapshot of the infant universe. By mapping the tiny temperature fluctuations in this radiation with exquisite precision, using satellites like Planck, cosmologists can deduce the fundamental ingredients of the cosmos, the amounts of ordinary matter, dark matter, and dark energy, as well as the geometry of the universe. Using our extremely well-tested model of cosmic evolution, known as the lambda cold dark matter model, they can then run the cosmic film forward from the early universe to the present day and predict what the Hubble constant should be right now. This method is like determining how fast a runner is going now by examining a high-speed photograph taken at the starting line and knowing the exact incline and friction of the entire track. The problem, the core of the Hubble tension, is that these two methods, after decades of ever more precise measurements, stubbornly refuse to agree. The local distance ladder method, championed by teams like the one led by Nobel laureate Adam Rees, gives a higher value for the Hubble constant. The early universe method from the Planck satellite collaboration gives a lower value. The difference between them is not large in everyday terms, only a few kilometers per second per megaparsec, but given the incredible precision of each measurement, the gap is statistically significant. It's not a small error or a blip, it's a persistent and growing discrepancy. It's as if two of the world's most accurate clocks, built by master craftsmen using different but equally valid principles, started ticking at slightly different rates. At first, you might blame a mechanical flaw, but when both clocks are checked and rechecked and both are found to be perfectly made, you are forced to consider a more radical possibility. That time itself might not be what you think it is. This is the profound implication of the Hubble tension. The disagreement suggests that there might be something fundamentally wrong or incomplete about our standard model of cosmology. Perhaps our understanding of dark energy is too simple. Maybe it's not a constant cosmological force, but something that evolves over time, changing strength in a way we haven't accounted for. Or perhaps dark matter has properties we haven't yet discovered. Maybe it can interact with itself or with light in very subtle ways that would alter the universe's expansion history. Another tantalizing possibility involves the early universe. What if there was a brief early episode of dark radiation, caused by an unknown, fast-moving particle that would have changed how quickly the early universe expanded, thereby shifting the CMB's prediction for the present-day expansion rate. Some have even speculated about more exotic ideas, such as the existence of a dark magnetism, or that our local region of the universe is part of an underdense bubble, making our local measurement unrepresentative of the cosmos as a whole. The Hubble tension is more than just a technical disagreement over a number. It is a gravitational riddle that challenges the consistency of our cosmic story. It forces us to ask whether the universe we see nearby is truly connected to the universe we see in its infancy by the simple, elegant rules we have written. Resolving this tension is one of the highest priorities in cosmology today, because whatever the solution turns out to be, a systematic error in one of the measurements, or a thrilling discovery of new physics, it will undoubtedly lead to a deeper and more complete understanding of the cosmos, its contents, and its ultimate destiny. This fundamental uncertainty about the very expansion of space finds a curious echo in another anomaly imprinted on that ancient light from the beginning of time, a mysterious cold spot that might be a window into one of the largest structures ever to exist. The cosmic microwave background is our most precious window into the universe's infancy, a fossilized echo of the Big Bang that has been traveling for over 13 billion years to reach us. This nearly uniform glow, visible in every direction as a faint hiss of microwave radiation, is the cooled remnant of the universe's fiery birth. Its temperature is remarkably consistent, varying by only tiny fractions of a degree across the entire sky. This smoothness is a cornerstone of our cosmological models, a testament to a period of ultra-fast expansion called inflation that ironed out the primordial wrinkles. But when astronomers created exquisitely detailed maps of this background, most notably with the Planck satellite, they spotted something that shouldn't be there. In the southern hemisphere, nestled within the constellation Eridanus, lies a large and significantly colder patch. This is the CMB Cold Spot, an anomaly so pronounced that it stands out against the otherwise uniform tapestry of the early universe. It's not just a little bit chilly, it is a substantial deviation, a cosmic cold sore that has resisted easy explanation. One of the leading theories to explain this chill involves a phenomenon that connects the very large to the very old, a gravitational effect that imprints the structure of the modern universe onto the ancient light from its beginning. The idea is that the cold spot might not be a feature of the CMB itself, but rather a shadow cast by a vast, largely empty region of space between us and the surface of last scattering, the distant wall where the CMB originated. Such a region is known as a supervoid, a cosmic desert spanning hundreds of millions of light years. But how could an absence of matter make ancient light appear colder? The answer lies in a subtle but powerful effect predicted by general relativity called the integrated Sachs-Wolf effect. To understand it, imagine a photon of light from the CMB embarking on its long journey toward Earth. For most of its travel, it is passing through a universe where the large-scale distribution of matter is relatively static. The gravitational wells it enters are just as deep as the ones it leaves. There's no net energy change, however, in a universe that is not only expanding but accelerating in its expansion due to dark energy. This balance is broken. When a photon enters a region of high density, like a galaxy cluster, it must climb out of a deep gravitational well. This costs it energy, causing it to redshift, which we perceive as a slight cooling. Conversely, when a photon travels through an underdense region, a void, it is actually climbing out of a shallower well than it entered. The gravitational potential is changing because dark energy is causing the void to become even emptier and the surrounding dense regions to become even more distinct over cosmic time. As the photon exits the void, it finds itself having gained a tiny amount of energy. This might sound like it should make the light hotter, but in the context of the CMB, the effect is framed relative to the average. The key point is that the photon's journey through an evolving gravitational landscape leaves an imprint. When we look at the CMB through a supervoid, the net effect of this complex gravitational interaction is a very slight loss of energy for the photons, making that particular patch of the sky appear cooler than its surroundings. The cold spot in this scenario would be the shadow of one of the largest structures in the universe, a colossal bubble of nothingness. The hunt for this hypothetical supervoid has been a major astronomical endeavor. If it exists, it would be a structure of truly staggering proportions, perhaps 500 million to a billion light-years across. Finding an absence of something is paradoxically much harder than finding a presence. Astronomers have indeed identified a large underdense region in the general direction of the cold spot, but the evidence remains controversial. The void they found seems significant, but many scientists argue it is not nearly large enough or empty enough to account for the pronounced coldness observed in the CMB. The discrepancy between the size of the proposed void and the strength of the cold spot effect is a serious challenge to this otherwise elegant explanation. This has led to more speculative and far more thrilling possibilities. Could the cold spot be evidence of something truly exotic? Some theorists have proposed that it might be a signature of a collision between our universe and another bubble universe in the vast landscape of the multiverse. In this mind-bending scenario, the cosmic bruise left by such an impact could have created a localized region of unusual physics, imprinting a cold signature on the CMB. While this is an exciting idea, it remains highly speculative and is considered a last resort, only to be invoked if all conventional explanations fail. The cold spot, therefore, remains an open case. It is a tantalizing puzzle that sits at the intersection of the very old and the very large. It challenges us to better understand the subtle gravitational interplay between dark energy and the cosmic web, and it pushes our observational capabilities to their limits as we search for the faint outlines of these immense voids. Whether it is ultimately explained by a gargantuan emptiness or by something even more profound, it serves as a powerful reminder that even the most uniform and well-understood phenomena in the cosmos can harbor deep secrets. This mysterious imprint of cold on the universe's first light stands in stark contrast to the next wonder we will explore, where the mystery is not an absence, but a presence that appeared far too early and grew far too quickly. Just as the cold spot presents a puzzle of coldness in the ancient sky, our next gravitational wonder confronts us with a presence of overwhelming heat and power that arrived impossibly early in the cosmic story. We now journey to the very dawn of the universe, to an era when the first stars and galaxies were only just beginning to ignite, and we find there a paradox of staggering proportions. Supermassive black holes that were already ancient giants in a cosmic infancy. According to our standard understanding of black hole growth, these cosmic predators should start small. A massive star ends its life in a supernova, collapsing its core into a black hole perhaps 10 or 20 times the mass of our Sun. This stellar mass seed then begins a slow, patient process of growth. It must lurk in the heart of a galaxy, merging with other small black holes, and most importantly, feasting on a continuous diet of gas over billions of years. This process of accretion is governed by physical limits. There's only so much material a black hole can swallow at a time before the intense radiation from the heated infalling gas pushes back and limits its meal. It's a gradual climb from tens of solar masses to the millions or billions required to become a supermassive black hole, a journey that should take a significant fraction of the universe's lifetime. Yet, when astronomers point our most powerful telescopes, like the James Webb Space Telescope, back in time to when the universe was less than 1 billion years old, a mere 7% of its current age, they see something that shatters this gradualist timeline. They find quasars, the incredibly bright, active nuclei of galaxies, powered by black holes that already weigh over 1 billion times the mass of our Sun. It is the cosmic equivalent of discovering a fully grown, towering redwood tree in a forest that was only just planted a few seasons ago. The existence of these primordial leviathans presents a profound challenge. How could an object accumulate so much mass in such a cosmically short amount of time? The math simply doesn't work with the standard model. Even if a black hole started feasting immediately after the first stars formed and ate at the maximum possible rate allowed by physics, it would struggle to reach such immense proportions in under 1 billion years. This forces us to consider that the seeds for these monsters must have been born different, or that the rules of the game in the early universe were radically altered. One compelling theory to solve this mystery involves skipping the stellar death step entirely. Instead of forming from a single star, perhaps the first black holes were born big as colossal seeds. This idea, known as direct collapse, envisions a unique environment in the early cosmos. Before the first stars had fully polluted the universe with heavy elements, vast clouds of pure hydrogen and helium could have existed. Under the right conditions, a particularly massive and dense cloud, perhaps destabilized by the gravitational pull of a nearby galaxy, could have begun to collapse. But instead of fragmenting into many individual stars as clouds do today, it could have collapsed as a single, monolithic entity. With no heavy elements to help it cool and fragment, the cloud would have fallen inward catastrophically, directly forming a black hole with a starting weight of 10,000 to 100,000 solar masses. This is not a stellar seed. This is a supermassive seedling, giving it a colossal head start in the growth race. From this massive baseline, it could then accrete gas at a ferocious pace to become a billion solar mass giant within the available time. Another fascinating possibility is that the early universe provided a perfect feast for these growing black holes. The conditions shortly after the first stars formed were incredibly rich with dense, cold gas, the perfect fuel for accretion. Perhaps these early black holes were able to eat in a way that is impossible in the modern universe. They might have experienced sustained periods of super-Eddington accretion, where the inflow of gas is so dense and chaotic that it overwhelms the radiation pressure that normally acts as a brake. Imagine trying to put out a bonfire with a fire hose. The sheer volume of material can push through the heat. In the turbulent, gas-rich nurseries of the first galaxies, such feasting frenzies might have been common, allowing black holes to pack on mass at an astonishing rate. Furthermore, the frequent mergers of small, young galaxies in the crowded early universe would have consistently funneled fresh gas toward the central black hole, keeping the banquet table full. It's a scenario where the black holes didn't just have bigger seeds, they were raised in an all-you-can-eat cosmic buffet that closed down after the first few billion years. The discovery of these ancient giants does more than just rewrite the life story of black holes. It forces a profound rethinking of the relationship between a galaxy and its dark heart. We now know that in the modern universe, the mass of a galaxy's central black hole is closely correlated with the mass of its central bulge of stars. This suggests that the growth of the black hole and the growth of the galaxy are intimately linked, a process known as co-evolution. The existence of billion solar mass black holes in infant galaxies implies that this relationship was established incredibly early. The gravitational influence of these behemoths must have been a dominant force from the very beginning, shaping the formation of the first stars and regulating the growth of their host galaxies through powerful outflows of energy. They were not passive residents, they were active architects, their immense gravity controlling the destiny of the galaxies they called home. Unraveling the mystery of their rapid growth is therefore key to understanding how all large galaxies, including our own Milky Way, came to be. The sheer energy required to power these early quasars points us toward the next cosmic spectacle, where the death of a star is not an end but a transformation into one of the most brilliant and mysterious events in the universe. The death of a star is one of the universe's most violent and energetic events, a final, defiant blaze of glory that can outshine an entire galaxy. We call this a supernova. But what happens when a supernova isn't just brilliant, but is hundreds of times brighter than it has any right to be? This is the realm of the superluminous supernova, a cosmic explosion so outrageously powerful that for years its very existence defied explanation. A typical supernova, the kind produced when a massive star exhausts its fuel and collapses, releases a staggering amount of energy, equivalent to the total output of our Sun over its entire 10 billion-year lifetime, all compressed into a matter of weeks. To imagine something hundreds of times brighter than that is to venture into the territory of the truly extreme. For a long time, astronomers were baffled. What possible engine could generate such an incredible, sustained outpouring of light? The leading theory that has emerged to solve this mystery is as elegant as it is powerful, and it centers on a special kind of stellar corpse born in the heart of the cataclysm. The story begins not with the explosion itself, but with the object it leaves behind. When a very massive star, perhaps dozens of times heavier than our Sun, reaches the end of its life, its core collapses under its own immense gravity. In a standard supernova, this collapse results in the formation of a neutron star or a black hole, and the rebound shockwave blasts the star's outer layers into space. But for a superluminous supernova, the outcome is even more specific. Theorists propose that under the right conditions, the collapsing core can form a particular type of neutron star known as a magnetar. A magnetar is a neutron star on steroids. It has the same incredible density, but it is also endowed with a magnetic field of almost unimaginable strength. We are talking about a field that is 1,000 trillion times more powerful than Earth's magnetic field. A magnetar's field is so strong that if one were located halfway between the Earth and the Moon, it would effortlessly wipe the data from every credit card on our planet. This newborn magnetar is not just immensely magnetic, it is also born spinning at a dizzying rate, completing a full rotation in just a few milliseconds. And this is where the true power source for the superluminous supernova is revealed. A rapidly spinning object with an intense magnetic field acts like a gigantic dynamo, and as the magnetar's rotation gradually slows down, it loses rotational energy. This energy has to go somewhere. In the case of a superluminous supernova, that energy is not lost, it is transferred. The spinning down of the magnetar acts like a continuous engine, injecting a tremendous amount of extra energy into the expanding shell of debris from the initial explosion. It's the difference between a single stick of dynamite going off and that same dynamite being attached to a powerful, long-lasting booster rocket. The initial shockwave from the core collapse creates the supernova, but the magnetar's spin down provides the sustained afterburner that makes it superluminous. This extra energy heats the ejected material, causing it to glow with an extraordinary brilliance that can persist for months, far outshining a normal supernova. This model provides a beautiful and physically plausible explanation. but the universe always enjoys presenting us with alternatives. Another compelling theory suggests that some superluminous supernova could be powered by a different, even more extreme mechanism: the collision of the supernova ejector with a massive shell of material that the star shed in a violent outburst just before its death. In this scenario, the star doesn't die quietly. In its final years or centuries, it might experience immense eruptions, casting off huge amounts of its own outer layers. When the core finally does collapse and the supernova shockwave erupts outward, it slams into this pre-existing shell of gas at incredible speeds. The resulting collision converts an enormous amount of kinetic energy into heat and light, creating a display that rivals the magnetar model. Determining which mechanism is at work requires careful detective work, analyzing the light curve, how the brightness changes over time, and the spectrum of the explosion to look for the chemical fingerprints of the processes involved. Some events clearly point to a central engine like a magnetar, while others show evidence of interaction with circumstellar material. It's likely that both pathways, and perhaps others we haven't yet imagined, can lead to these spectacular cosmic fireworks. The study of superluminous supernova does more than just satisfy our curiosity about stellar death throes. It serves as a crucial probe of the early universe. Because they are so incredibly bright, they can be seen at phenomenal distances, acting as beacons that illuminate the cosmos when it was very young. They offer a way to study the first generations of stars, which were likely very massive and may have died in explosions unlike anything we see today. Furthermore, the intense conditions within these events are thought to be factories for creating heavy elements, the very atoms that make up planets and life. The gravitational collapse that forges the magnetar is therefore not just an end, but a creative act of cosmic alchemy, seeding the universe with the raw materials for future worlds. The sheer power unleashed in these events is so immense that if one were to occur within our own galaxy, even thousands of light years away, it would be visible in the daytime sky and could potentially affect Earth's atmosphere. Thankfully, such events are exceedingly rare in mature galaxies like our own. They are a testament to gravity's dual role as both a destroyer and a creator, capable of ending a star's life in a way that illuminates the cosmos for billions of years to come. But of all the strange things gravity can do to light, perhaps the most visually stunning and geometrically perfect is the phenomenon known as an Einstein ring. It sounds like something from a science fiction novel, a halo of light hanging in the depths of space, and yet it is a very real and powerful confirmation of a prediction made by Albert Einstein over a century ago. The concept is rooted in his theory of general relativity, which tells us that mass warps the fabric of space-time. Now, imagine a perfectly straight line drawn on a stretched rubber sheet. If you place a heavy weight on that sheet, the line will curve around the indentation. Light, which always follows the shortest path through space-time, behaves in exactly the same way. It doesn't travel in a straight line as we classically think of it. It follows the curves created by massive objects. An Einstein ring is the ultimate expression of this bending, occurring under a very specific and rare cosmic alignment. Picture three objects in a perfect line. First, an observer on Earth. Next, a massive foreground object like a galaxy or a cluster of galaxies. And finally, a more distant galaxy or quasar are directly behind the foreground mass. The light from that distant background object travels outwards in all directions, but the paths that pass near the foreground mass get bent by its gravity. From our vantage point on Earth, this bending focuses the light, much like a magnifying glass. When the alignment is absolutely perfect, the light from the background source is bent into a complete circle around the foreground object. It's a cosmic bullseye, a ring of light that is not actually there, but is a mirage, a gravitational illusion of incredible precision. The existence of these rings was predicted by Einstein himself in 1936, but he was deeply skeptical that we would ever actually see one. He reasoned that the required alignment would be so exact, so astronomically improbable, that it was practically impossible to observe. For decades, it seemed he was right. But as our telescopes grew more powerful and our surveys of the sky became more extensive, we began to find them. The first complete Einstein ring was discovered in 1998, and since then we have found many more. Each one is a minor miracle of geometry, a testament to the sheer scale of the universe where even the most unlikely events eventually come to pass if you look at enough galaxies. The scientific value of these beautiful circles, however, goes far beyond their aesthetic appeal. They are, in essence, nature's own scales. By carefully measuring the size and shape of the ring, astronomers can perform a remarkable feat. They can weigh the foreground object that is causing the lensing. The more massive the lensing galaxy or cluster, the larger the ring will be. This provides a direct and powerful way to measure the total mass of these distant objects, including all the dark matter that we cannot see. An Einstein ring effectively allows us to map the gravitational field of the lens with exquisite detail, revealing the distribution of both visible and dark matter within it. It's one of the most direct tools we have for studying the invisible scaffolding of the cosmos. Furthermore, this gravitational lens acts as a natural telescope, and an incredibly powerful one at that. The bending of the light doesn't just create a ring, it magnifies the light from the background galaxy. This allows us to study galaxies that are so far away they would normally be far too faint and small to see in any detail. Through the cosmic lens of an Einstein ring, we can peer into the early universe, examining the structure of infant galaxies, their rate of star formation, and their chemical composition with a clarity that would otherwise be impossible. It's as if the universe has provided us with a series of gigantic, pre-positioned magnifying glasses, each one offering a free upgrade to our most powerful telescopes. While the perfect circle of an Einstein ring is the most iconic form of this phenomenon, it is also the rarest. The universe is a messy place, and perfect alignments are few and far between. More commonly, the background source, the lens, and the observer are slightly misaligned. In these cases, gravity creates not a perfect ring, but a collection of multiple, distorted images of the same background object. You might see 2 or 4, or even more stretched and magnified copies of a single distant galaxy arranged in a circular pattern around the central lens. These are known as gravitational arcs or mirages, and they are just as scientifically valuable, painting a more complex but equally informative picture of gravity's distorting power. While the perfect symmetry of an Einstein ring is a breathtaking sight, the universe more commonly offers us a gallery of distorted and fragmented masterpieces. When the cosmic alignment is not quite perfect, when the distant galaxy, the massive lensing cluster, and our line of sight are slightly off-center, gravity's artistry takes on a different form. Instead of a complete circle, we see long, shimmering streaks of light curving around the foreground cluster like great celestial brushstrokes. These are gravitational arcs, and they are just as scientifically profound as their more perfectly formed cousins. In the most extreme cases, the background galaxy can be stretched so dramatically that it appears as a thin, bright sickle, a mirage that can even wrap entirely around the central cluster, forming an almost complete ring. But the distortions can be even more bewildering. Because light can take multiple paths around the gravitational well of the cluster, all converging at our telescope, we often see multiple images of the same distant galaxy. It's not uncommon to find 2, 4, or even more ghostly copies of a single object arranged in a circular pattern around the lens, a cosmic hall of mirrors created by the warping of spacetime itself. The true power of these arcs and multiple images lies in their ability to act as a direct scale for the cosmos. They are not just pretty pictures, they are precision tools for weighing the universe's most massive structures. The exact shape, length, and brightness of an arc, along with the positions of the multiple images, are exquisitely sensitive to the distribution of mass within the lensing galaxy cluster. Think of it like looking at a street lamp through the bottom of a wine glass. By studying how the light is distorted, you could, in principle, map the exact contours of the glass. In exactly the same way, astronomers use the distorted images of background galaxies to map the gravitational potential of the foreground cluster. This allows them to calculate the cluster's total mass with remarkable accuracy. And here's the crucial part: when they compare this total mass, derived purely from gravity's effect on light, to the mass we can account for from the visible stars and hot gas within the cluster, there is a staggering discrepancy. The vast majority of the mass is completely invisible. The gravitational arcs are, therefore, one of the most direct and visually compelling pieces of evidence for the existence of dark matter. They show us that what we see in a galaxy cluster is just the glittering tip of a massive, dark iceberg. Beyond their role as cosmic scales, these gravitational mirages serve another, equally vital function. They are the universe's own natural telescopes. The same bending of light that distorts the images also magnifies them. A faint, distant galaxy that would be nothing more than an indistinct smudge in our most powerful telescopes can be stretched and amplified by a foreground cluster into a detailed, luminous arc that we can study in depth. This phenomenon, known as strong gravitational lensing, gives us a free upgrade to our observational capabilities. It allows us to peer back to the very earliest epochs of galaxy formation, to a time when the universe was only a few billion years old. Through these cosmic lenses, we can resolve the internal structure of these infant galaxies, measuring their rates of star formation, analyzing their chemical composition, and watching as they evolve in real time, albeit over cosmological timescales. Some of the most distant galaxies ever observed were only found because they were fortuitously magnified by a foreground cluster. Their light bent and focused onto our detectors like sunlight through a magnifying glass. This transformative power turns every massive galaxy cluster into a potential window to the ancient universe, a natural observatory that extends our vision to the very limits of space and time. The intricate patterns formed by these arcs and multiple images are more than just random distortions. They are a precise map of the invisible gravitational landscape of the cluster. The way the light bends reveals the contours of the dark matter halo, tracing out its shape and density in a way that no other method can. By carefully analyzing these patterns with sophisticated computer models, astronomers can reconstruct a three-dimensional map of where the mass is concentrated. They can identify sub-halos of dark matter, the gravitational seeds around which individual galaxies within the cluster formed. This process is a form of cosmic cartography, using light as a probe to chart the topography of an unseen world. The resulting maps show that dark matter is not smoothly distributed but is clumped and structured, forming the skeletal framework upon which the visible universe is built. This ability to see the invisible through its gravitational influence is one of the most remarkable achievements of modern astronomy, a testament to the power of human ingenuity and the elegant rules that govern the cosmos. Yet, for all the dramatic clarity of these strong lensing effects, they represent only the most pronounced examples of gravity's light-bending power. The majority of the universe's mass reveals its presence not through giant arcs and mirrored images, but through a far more subtle and pervasive warping that requires a different kind of vision to see. While the dramatic arcs and perfect rings of strong gravitational lensing capture the imagination, they represent the exception rather than the rule in the cosmos. For every one of those spectacular cosmic mirages, there are millions upon millions of instances where gravity's touch is far more delicate, a gentle warping that doesn't shatter the image but merely whispers a subtle distortion. This is the realm of weak gravitational lensing, a phenomenon so faint that it is completely invisible to the human eye looking at any single galaxy. Imagine trying to discern the shape of a distant street lamp on a foggy night. The light is blurred and softened by the atmosphere, but you can still make out its general form. Now imagine that the lamp itself is perfectly round, but the fog distorts it ever so slightly, making it appear as a tiny, oval smudge. If you only had that one lamp to look at, you'd never be sure if the oval shape was real or just an effect of the haze. This is the fundamental challenge of weak lensing. The intrinsic shapes of galaxies are already diverse. Some are round, some are elongated, and others are irregular. How can you possibly detect a subtle, additional stretching caused by the gravity of invisible matter? The answer lies not in looking at one galaxy, but in looking at millions of them all at once. This is where weak lensing transforms from an imperceptible effect into one of the most powerful tools in all of cosmology. While any single background galaxy might be naturally elliptical, the direction of its elongation should be random when averaged over a vast swath of the sky. There is no reason for galaxies billions of light-years apart to all point in the same direction. However, if a vast cloud of dark matter lies between us and a whole population of these distant galaxies, its collective gravity will impose a coherent pattern on their apparent shapes. The light from each galaxy, as it passes through this invisible gravitational field, will be bent along a common direction, stretching each one in a similar orientation, like iron filings aligning to a magnetic field. The individual distortions are minuscule, far less than 1%, but by measuring the shapes of countless galaxies across a huge area of sky, sophisticated computer algorithms can detect this coherent statistical shearing. It's a monumental task of pattern recognition, finding a faint signal buried in a sea of natural randomness. The goal of this immense effort is nothing less than to create a map of the invisible. By meticulously measuring the subtle alignments of billions of distorted galaxies, cosmologists can reconstruct a three-dimensional chart of the dark matter that caused the distortions. It's akin to deducing the shape of a submerged mountain range by watching how it subtly alters the surface currents of the ocean above it. The resulting maps are breathtaking. They reveal the cosmic web in stunning detail, not as a theoretical concept, but as an observed reality. Vast filaments of dark matter stretch across the emptiness, connecting immense galaxy clusters at their intersections and enclosing giant voids where the gravitational pull is weakest. These maps confirm that dark matter forms the underlying skeleton of the universe, and the visible galaxies we see are merely tracing out its densest concentrations. The precision of these maps has reached such a level that they can even be used to weigh the most elusive component of the cosmos, dark energy. This is where weak lensing becomes a truly revolutionary probe. Dark energy, as the force driving the accelerated expansion of the universe, affects how cosmic structures grow over time. In a universe without dark energy, gravity would have had more time to pull matter together, making the cosmic web more clumpy and pronounced. The accelerated expansion, however, works against gravity, effectively pulling the universe apart and suppressing the growth of these large-scale structures. Weak lensing provides a way to measure this effect directly by comparing the strength of the lensing signal from the distant universe, which shows us the web as it was billions of years ago, to the lensing signal from the nearer universe, which shows us the web today. Astronomers can measure how the clustering of matter has evolved. The subtle differences in the maps over cosmic time provide a direct measure of the strength and nature of dark energy, offering clues as to whether it is a constant cosmological force or something that changes over time. Projects like the Vera-C, Rubin Observatory's legacy survey of space and time are designed to use weak lensing on an unprecedented scale, mapping the shapes of billions of galaxies to pin down the properties of dark energy with extraordinary precision. This statistical whisper, heard across billions of light years, is our best hope for understanding the force that will ultimately determine the fate of everything. For centuries, astronomers peering through their telescopes saw a sky dotted with galaxies, and it was natural to assume that these islands of stars were scattered more or less randomly throughout the vast, dark ocean of space. It was a simple, elegant picture, but as our technology advanced and we began to map the cosmos in 3 dimensions, a far more complex and magnificent truth emerged. We discovered that the universe is not a random scatter at all. It is structured on the grandest possible scale into an intricate, web-like architecture known as the cosmic web. This is not a metaphor, it is the actual large-scale structure of the cosmos, a pattern so vast that it defies human intuition. Imagine the neural network of a gigantic brain, or the frothy structure of a soap bubble bath, but on a scale where a single filament could take hundreds of millions of years for light to traverse. This is the gravitational skeleton of the observable universe, and its existence is one of the most profound confirmations of our models of cosmic evolution. The blueprint for this immense structure was drawn in the first fleeting moments after the Big Bang, during a period of incredibly rapid expansion called inflation. Tiny quantum fluctuations, smaller than a single atom, were stretched to astronomical sizes. These minute variations in density became the seeds for all future structure. After inflation ended, the universe was filled with a nearly uniform soup of matter and energy, but these seeds were embedded within it, regions that were ever so slightly denser than their surroundings. For hundreds of thousands of years, the intense pressure of radiation prevented gravity from getting to work. But once the universe cooled enough for atoms to form and light to travel freely, the era of structure formation began. Gravity, the universe's great sculptor, started its patient work. Over billions of years, it amplified those tiny initial differences. The slightly denser regions began to pull in more and more matter from their surroundings, growing steadily denser, while the less dense regions were gradually drained, becoming emptier. This process, acting across the entire cosmos, resulted in the distribution we see today. The cosmic web is a network of 3 primary components. First, there are the dense nodes, which are the massive galaxy clusters, the bustling metropolises of the universe where thousands of galaxies are gravitationally bound together. Then there are the filaments, the long, slender threads of dark matter and galaxies that form the bridges between these clusters, the cosmic highways connecting the urban centers. And finally, there are the voids, the vast, empty spaces that make up the majority of the universe's volume. These are the cosmic deserts, regions of astonishing emptiness that can span hundreds of millions of light years. The web is primarily made of dark matter, which provides the gravitational scaffolding. The ordinary matter, the gas and stars that we can actually see, simply follows this underlying dark matter structure, lighting up the web like fairy lights on a hidden wire frame. One of the most stunning validations of this theory comes not from direct observation, but from supercomputer simulations. cosmologists can program the laws of physics, including the effects of gravity, dark matter, and dark energy, into some of the world's most powerful computers. They can set the initial conditions to match those seen in the cosmic microwave background and then press play, allowing the simulation to run forward in time for over 13 billion years. The results are breathtaking. These simulations consistently produce structures that look almost identical to the maps we are now creating from observational data. They show the same web-like pattern, with filaments, clusters, and voids emerging naturally from the simple action of gravity on the primordial seeds. This remarkable agreement between simulation and observation is a powerful sign that we are on the right track in understanding the basic story of cosmic evolution. Actually observing this web directly, however, is a monumental challenge. Because we are inside the web, seeing its full structure is like trying to map the streets of a vast city while standing in the middle of one of its parks. For decades, the evidence was indirect, pieced together from painstaking surveys that mapped the positions of millions of galaxies. Today, new techniques are allowing us to see the web more clearly than ever before. We can now map the dark matter filaments themselves using the weak gravitational lensing effect, watching how their gravity distorts the light from billions of background galaxies. We can also observe the faint glow of hot gas that has been heated to millions of degrees as it falls into the filaments, a phenomenon known as the Sunyaev-Zeldovich effect. These observations are gradually filling in the lines of the cosmic cartographer's map, revealing the invisible architecture that dictates the flow and distribution of galaxies. The cosmic web is the ultimate expression of gravity's creative power, a structure built over eons that defines the landscape of the entire cosmos. And within this vast network, at the intersections of the thickest filaments, we find environments where the rules of physics are pushed to their absolute limits, places where galaxy clusters engage in collisions of unimaginable violence. Now, after exploring the vast, invisible architecture of the cosmic web, we arrive at a specific location where this hidden structure was laid bare in the most dramatic fashion imaginable. This is the story of the Bullet Cluster, a place in the sky where two entire families of galaxies, each containing hundreds of members, have slammed into one another in a collision of cosmic proportions. The aftermath of this incredibly violent event, far from being a confusing mess, has provided astronomers with what many consider to the most direct and compelling evidence for the existence of dark matter. It's a cosmic crime scene, and by examining the evidence left behind, we can identify the prime suspect, an invisible one that makes up the vast majority of the mass in the universe. To understand the evidence, we need to look at the different components of a galaxy cluster. A cluster isn't just a swarm of galaxies, it's a huge reservoir of extremely hot gas that fills the space between them. This gas is so hot, reaching temperatures of millions of degrees, that it glows brightly in X-ray light. Then, of course, there are the galaxies themselves, each containing billions of stars. And finally, according to our models, there is the immense halo of dark matter that holds the entire structure together. In a quiet, undisturbed cluster, these three components, the galaxies, the hot gas, and the dark matter are all co-located, mixed together in the same region of space. It's impossible to tell them apart, but a high-speed collision changes everything because each component behaves differently under the stress of impact. The Bullet Cluster is the result of two clusters that have recently passed through each other. Think of it not as a head-on car crash, but more like two clouds of smoke colliding. When this happened, the different parts of the clusters responded in their own unique ways. The galaxies, which are mostly empty space, are like the tiny, solid particles within the smoke clouds. They are so far apart that they sailed right past each other with almost no interaction, continuing on their trajectories largely unaffected. The hot gas between the galaxies, however, is a different story. This gas is a tangible, interactive substance. As the two clouds of gas smashed together, they created immense ram pressure, a frictional force similar to the resistance you feel when sticking your hand out of a moving car window. This interaction was so violent that it slowed the gas down dramatically, causing it to pile up and become compressed in the center of the collision. This pile-up is clearly visible as a bright, bullet-shaped cloud of X-ray emission, which gives the cluster its name. So, after the collision, we have a clear separation. The galaxies from both clusters have moved ahead, largely unscathed on either side of the impact zone. The gas, however, has been left behind, stuck in the middle. Now, here is the crucial part. If all the mass in the clusters were in the form of stars and gas, the majority of the gravitational force should be located where the majority of the visible matter is, which is in the central region with the piled-up gas. But that's not what astronomers observed when they mapped the cluster's total mass using the technique of gravitational lensing. By measuring how the cluster's gravity distorted the light from even more distant galaxies behind it, they could create a precise map of where the mass actually was. The result was stunning. The peak of the gravitational field was not in the center with the gas. Instead, it was located precisely where the galaxies were, ahead of the collision on either side. This meant that most of the mass had, like the galaxies, passed right through the collision without slowing down. This is the proverbial smoking gun. The only way to explain this observation is if the majority of the mass in the clusters is in a form that does not interact with itself or with ordinary gas. It felt the gravitational pull, so it stayed with the galaxies, but it did not feel the ram pressure that slowed down the gas, because it doesn't experience the electromagnetic force that causes such friction. This is exactly the property we attribute to dark matter. Dark matter particles, whatever they are, would be oblivious to the gas pile up. They would simply pass through each other and continue on their way, their location betrayed only by their gravitational influence. The bullet cluster effectively allowed us to see the dark matter separated from the normal matter for the first time. It's a clean, elegant, and powerful demonstration that most of the universe's substance is something we cannot see, a shadowy component that guides the motion of the stars and galaxies but remains forever hidden from our telescopes. This clear separation of mass from light is a landmark in modern cosmology, but as is often the case in science, the very next discovery showed that the story might not always be so straightforward. If the bullet cluster provided a seemingly clear and elegant proof for the existence of collisionless dark matter, then the merging galaxy cluster known as Abel 520 is the confounding sequel that forces us to question the simplicity of that story. Just when astronomers thought they had a firm grasp on how dark matter behaves in the most violent of cosmic environments, Abel 520 presented a puzzle that seemed to contradict the very rules the bullet cluster had helped to establish. It's a reminder that the universe often delights in presenting us with exceptions that challenge our most cherished models. While the bullet cluster showed a clean separation between the dark matter, which stayed with the galaxies, and the ordinary matter, which lagged behind, Abel 520 revealed a scene that was far more chaotic and difficult to interpret. Here, in the aftermath of a colossal pile-up of galaxy clusters, the map of mass created by gravitational lensing revealed something deeply strange. A significant concentration of dark matter, a gravitational hotspot, located in a region of space that was largely empty of galaxies. Astronomers dubbed this feature the dark core, a term that evokes a sense of mystery and something fundamentally out of place. This discovery was unexpected because of a key assumption in our understanding of how dark matter operates. We believe that galaxies form at the peaks of the dark matter distribution. The immense gravitational wells of dark matter halos are what draw in the gas that eventually forms stars and galaxies. Therefore, we expect the visible galaxies and the invisible dark matter to be closely tied together, like riders on a gravitational wave. In the bullet cluster, this relationship held true even during a collision. But in Abel 520, that connection appears to have been broken. The dark core is a pocket of immense gravity with no corresponding glitter of stars to explain it. It's as if you were investigating a traffic accident and found a massive, heavy object lying in the middle of the road, but all the cars involved had already moved far away from the impact site. What kind of object could be so heavy yet completely detached from the vehicles themselves? This anomaly has sparked intense debate and led to several compelling and sometimes conflicting hypotheses. One of the most intriguing possibilities is that the dark core is evidence that dark matter might not be entirely collisionless after all. Perhaps dark matter particles can interact with each other through a force other than gravity, a so-called non-gravitational interaction. In this scenario, during the complex, multi-body collision of clusters in Abel 520, this self-interaction could cause the dark matter to slow down and become stuck in the center of the merger, much like the hot gas did. The galaxies, which are mostly empty space and thus don't interact strongly, would have simply sailed through this region and continued on their way, leaving their dark matter anchors behind. If true, this would be a revolutionary discovery, revealing a new facet of dark matter's nature that goes beyond the simple, non-interacting particle model. However, not all astronomers are convinced that we need to invoke new physics to explain Abel 520. Alternative explanations focus on the sheer complexity of the merger event itself. Unlike the relatively clean binary collision of the bullet cluster, Abel 520 might have been a messier, multi-stage collision involving 3 or more galaxy clusters. In such a chaotic environment, the gravitational dynamics become incredibly complicated. It's possible that the dark core is not a single, coherent clump of dark matter, but a temporary superposition of dark matter from the different colliding subclusters, a gravitational illusion created by our two-dimensional view of a three-dimensional catastrophe. Another possibility is that a large number of faint, low-surface brightness galaxies are present in the core region, but are simply too dim for our current telescopes to detect. These unseen galaxies could be hosting the dark matter, preserving the standard model but hiding the visible evidence from our view. The truth is, Abel 520 remains an open case file in the annals of cosmology. It stands as a crucial counterpoint to the bullet cluster, a cautionary tale against drawing overly simplistic conclusions from single observations. It shows us that the behavior of dark matter in these extreme, high-energy environments is not yet fully decoded. Each merging cluster is a unique natural experiment, and by studying a whole population of them, we can hope to discern the underlying rules from the chaotic outcomes. Abel 520 doesn't disprove dark matter. Instead, it challenges us to understand its properties in greater depth. Is it a simple, cold, and non-interacting particle, or does it have a richer, more complex physics that only reveals itself during the most violent events in the universe? The dark core is a gravitational enigma that ensures the story of dark matter is still being written, a mystery that bridges the gap between the cosmic scale of galaxy clusters and the fundamental question of what the universe is truly made of. From the immense, galaxy-shattering collisions of dark matter halos, we now journey inward to a realm of almost unimaginable smallness, where the rules governing the universe's largest structures are put to the test on a scale 1,000,000,000 times smaller than a grain of sand. It may seem a dramatic leap, but this is where we find a mystery that is just as profound as any cosmic void or dark core. This is the proton radius puzzle, a discrepancy so tiny and precise that its very existence threatens to reveal a crack in the foundation of modern particle physics. For decades, we thought we had a very good handle on the size of a proton, one of the fundamental building blocks of every atom in your body, in every star, in everything we see. The proton is not a single point-like particle. It's a fuzzy cloud of quarks and gluons, and its size can be defined by its charge radius, essentially the reach of its positive electric charge. Scientists had measured this radius for years using hydrogen, the simplest atom, which consists of a single electron orbiting a single proton. By studying the specific energy levels or orbitals that the electron can occupy, physicists could calculate the proton's size with impressive accuracy, arriving at a well-established and accepted value. The puzzle emerged when physicists decided to perform a more precise version of this experiment, but with a crucial twist. Instead of using a normal electron, they created an exotic atom called muonic hydrogen. A muon is a fundamental particle that is identical to an electron in every way except one. It's about 200 times heavier. This greater mass is the key to the entire mystery. In a hydrogen atom, the electron orbits far from the proton, like a distant moon around a planet. Because it's so light, its orbit is wide, and it only gently probes the proton's size. But when you replace the electron with a much heavier muon, everything changes. The muon's greater mass means it is drawn into a much tighter orbit, pulling it incredibly close to the proton. It's like swapping that distant moon for a satellite in a low, fast orbit skimming the planet's atmosphere. This muon orbits so close that it becomes exquisitely sensitive to the proton's finite size, acting as a powerful, natural microscope for probing the proton's structure. When an international team of researchers measured the energy levels of muonic hydrogen with breathtaking precision, they expected to confirm the proton radius obtained from decades of electronic hydrogen experiments. Instead, they found a shocking discrepancy. The radius they measured was significantly smaller, about 4% smaller, than the accepted value. While 4% may sound trivial in the world of subatomic precision, it's a chasm. The two results were separated by a staggering 5 standard deviations, a level of certainty that in particle physics qualifies as a definitive discovery, not a statistical fluke. This was the birth of the proton radius puzzle. How could the same proton appear to have two different sizes depending on which particle was orbiting it? It was as if you measured a room with a tape measure and got one result, but then measured it with an even more precise laser rangefinder and found the room was noticeably smaller. One of the measurements had to be wrong, or something fundamentally new was at play. The immediate assumption was that there must be a hidden error, an unaccounted for systematic effect in the complex muonic hydrogen experiment. But years of intense scrutiny have only reinforced the result. Meanwhile, new experiments with regular electronic hydrogen using advanced techniques have largely confirmed the older, larger value for the proton radius, deepening the mystery. This persistent disagreement points to a thrilling possibility that we are seeing a signature of physics beyond the Standard Model. The Standard Model is our incredibly successful catalog of fundamental particles and forces, but it is known to be incomplete. It does not, for example, include gravity. Perhaps the muon, due to its greater mass, is sensitive to a new, previously unknown force of nature, a fifth force that interacts differently with muons than it does with electrons. This force would be extremely short range, acting only over the tiny distance between the muon and the proton, which is why it would be invisible in experiments with ordinary electrons. The muon, by orbiting so close, is essentially our only window into this hidden realm of particle interactions. While this puzzle is not directly about gravity in the way the orbit of a planet is, it shares a profound philosophical connection with the gravitational wonders we've explored. It is another example of a precise measurement revealing an anomaly that our current theories cannot explain. Just as the galaxy rotation problem pointed to dark matter and the accelerating universe pointed to dark energy, the proton radius puzzle points to something missing from our understanding of the fundamental forces. Some theoretical physicists have even speculated that the solution could have implications for gravity itself, perhaps relating to how gravity behaves at these infinitesimal scales, or how it might be integrated with the other forces. The puzzle is a powerful reminder that the laws of physics must be universal. They should work the same for a muon as they do for an electron, and they should be consistent from the heart of the atom to the vast expanse of the cosmic web. When they are not, it is not a failure but an invitation to a deeper discovery. This tiny discrepancy in the size of a single particle echoes a much larger and more fundamental imbalance in the forces that shape our reality, an imbalance so extreme that it challenges our very understanding of why the universe is structured the way it is. We have now explored the universe from the scale of colliding galaxy clusters down to the puzzling size of a single proton. But our next gravitational wonder strikes at a mystery so fundamental that it underlies every single phenomenon we have discussed so far. It is a question that might seem simple at first, but its implications are arguably the deepest in all of physics. Why is gravity so unbelievably, astoundingly weak? To truly appreciate just how feeble gravity is, consider a simple, everyday experiment. You can easily lift a small metal paperclip off your desk with a tiny refrigerator magnet. In that moment, the electromagnetic force generated by that little magnet is effortlessly overcoming the combined gravitational pull of the entire planet Earth. The strength difference is not just large, it is astronomical. The electromagnetic force is roughly 10 to the power of 36 times stronger than gravity. That is a 1 followed by 36 zeros, a number so vast it defies any meaningful analogy. You could say that the difference in strength between gravity and electromagnetism is 1 trillion times greater than the difference in strength between a single atom and the entire sun. This mind-boggling disparity is known as the hierarchy problem. The problem is not just that the forces have different strengths, it is that this difference is so unimaginably huge. In the world of particle physics, forces are mediated by particles. Electromagnetism is carried by the massless photon. The strong nuclear force, which holds atomic nuclei together, is carried by gluons. These forces are strong. Gravity, according to our best theory, should be mediated by a hypothetical particle called the graviton. But for the graviton to produce such a weak force, its influence would have to be dialed down by that factor of 10 to the 36. Why? What possible mechanism in nature could create such an enormous gap between the fundamental interactions? One possibility is that it is simply a random, anthropic accident. This line of reasoning, known as the anthropic principle, suggests that if gravity were even a little bit stronger, the universe would be radically different and likely incapable of supporting life. Stars would burn out much faster, planets would be crushed, and complex structures could never form. In this view, we find ourselves in a universe with a weak gravitational force simply because we couldn't exist in one where it was stronger. While this might be true, it feels deeply unsatisfying to most physicists who seek a more dynamic, mechanistic explanation for the laws of nature. this search has led to some of the most fascinating and ambitious ideas in theoretical physics. One particularly compelling concept involves the nature of space itself. What if our universe has more than the three spatial dimensions we experience? String theory, for instance, requires the existence of several extra, tiny, curled-up dimensions. This opens up a breathtaking possibility for solving the hierarchy problem. Imagine that gravity is not inherently weak. What if, in its native realm, gravity is just as strong as the other forces? The proposal is that while the particles of the standard model, like electrons and quarks, are confined to our familiar three-dimensional space, the graviton can leak out into these extra dimensions. From our limited three-dimensional perspective, the strength of gravity would appear diluted, spread thin across all the dimensions it inhabits. It would be like comparing the force of a water jet from a hose to the gentle, widespread mist from a garden sprinkler. The water pressure at the source might be the same, but its effect in any one area is much weaker when it is dispersed. In this scenario, gravity only seems feeble because we are not seeing its full, concentrated power. The Large Hadron Collider has searched for evidence of these extra dimensions by looking for missing energy as particles potentially vanish into them, but so far, no definitive signal has been found. Another major theoretical framework proposed to solve this problem is supersymmetry, often abbreviated as SUSY. This elegant idea posits that every known fundamental particle has a superpartner, a yet-to-be-discovered twin with a different spin. One of the many attractive features of supersymmetry is that it could naturally stabilize the vast gap between the force strengths, preventing quantum corrections from making the Higgs boson's mass, and by extension the weakness of gravity, unstable and unnaturally fine-tuned. If supersymmetry were true, these superpartners should have been produced in particle colliders, but despite extensive searches, not a single one has been detected. This has forced physicists to consider that if supersymmetry is a property of our universe, the superpartners must be much heavier than originally hoped, making them more difficult to produce and detect. The continued absence of evidence for either extra dimensions or supersymmetry means the hierarchy problem remains a wide open and deeply puzzling question. The profound weakness of gravity, while a theoretical headache, is also a blessing. It is this very feebleness that allows for the existence of the universe as we know it. Because gravity is so weak, it takes an absolutely colossal amount of matter to create a significant gravitational pull. This is why planets, stars, and galaxies can be so vast. It allows for the existence of stable, long-lived orbits, like Earth's gentle revolution around the Sun, which provides the stable environment necessary for life to evolve over billions of years. If gravity were even 100 times stronger, stars would burn through their fuel in a cosmic blink, and any planetary orbits would be wildly unstable. The hierarchy problem, therefore, is not just an abstract puzzle for physicists. It is intimately connected to our own existence. The fact that we can even ponder this question is a direct consequence of gravity's gentle touch. This delicate balance, which allows for stable solar systems and the possibility of life, finds a fascinating echo in a historical paradox involving our own sun, a puzzle where a seemingly weak young star should have created a frozen Earth, but instead gave rise to a world ripe for life. The story of our solar system's habitability begins not with the Earth itself, but with the star at its center. We tend to think of the sun as a constant, unwavering beacon, but like all stars, it has a life story. And in its youth, our sun was fundamentally different. Billions of years ago, when the Earth was still a young world and the first tentative steps toward life were being taken, the sun was significantly dimmer. Nuclear fusion in its core was still getting up to speed, and as a result, it shone with only about 70% of the luminosity it has today. If you could travel back in time to the Archean Eon, around 3.5 billion years ago, the Sun would have appeared noticeably smaller and paler in the sky. This presents a profound puzzle, one that astronomers and geologists call the faint young sun paradox. The logic is straightforward and deeply troubling. If we take our current understanding of stellar evolution as correct, and we also accept our modern models of planetary climate, then a simple calculation leads to an inescapable conclusion. The early Earth should have been a global ice ball. With 30% less energy arriving from the Sun, the planet's surface temperatures would have been well below the freezing point of water. The oceans should have been frozen solid from pole to pole, creating a world encased in a thick, reflective shell of ice that would have bounced even more sunlight back into space, locking the planet into a permanent, deep freeze. Such a state would have made the origin and evolution of life, as we know it, effectively impossible. Yet, the geological record screams a very different story. Ancient rocks from that very period, some of the oldest on Earth, tell us unmistakably that liquid water was abundant. We find evidence of sedimentary deposits that could only have been laid down by flowing water, and pillow lavas that formed when lava erupted under an ocean. Most tellingly, we have fossilized remains of microbial life that date back to this time. The Earth was not frozen. It was a watery world, likely even warmer than it is today, with a climate hospitable enough for life to not only begin but to thrive. So, what was keeping the planet warm when the Sun was so faint? How did Earth avoid becoming a permanent snowball? The most widely accepted solution to this paradox points to a very different kind of atmosphere on the early Earth. Our planet today has an atmosphere that is mostly nitrogen and oxygen, with a small amount of carbon dioxide and other greenhouse gases that provide a crucial warming effect. But back then, the atmosphere was likely much richer in potent greenhouse gases like carbon dioxide and methane. Think of these gases as a celestial blanket. The faint sun provided less heat, but a thicker blanket trapped that heat more effectively near the surface. Methane, in particular, is a tremendously powerful greenhouse gas, and it is believed that early methanogenic microbes may have been pumping vast quantities of it into the air, creating a supercharged greenhouse effect that compensated for the solar shortfall. Another compelling theory involves the complete absence of oxygen, which would have prevented the formation of an ozone layer. This would have allowed more of the sun's ultraviolet radiation to reach the lower atmosphere, potentially helping to create a photochemical smog that also contributed to warming. But while the atmospheric explanation is crucial, it overlooks a more fundamental and delicate factor: gravity. The very possibility of maintaining a stable, life-friendly atmosphere over billions of years hinges on a precise gravitational balance. Earth's mass, dictated by the amount of material that coalesced in its orbit around the young sun, generates just the right amount of gravity to hold onto an atmosphere of the correct density and composition. A smaller planet like Mars with weaker gravity saw its atmosphere slowly stripped away by the solar wind, leaving it a barren desert. A more massive planet might have held onto an atmosphere so thick and crushing that its surface would be uninhabitable. This gravitational fine-tuning extends directly to our orbit. The Earth's path around the Sun is not a perfect circle, but it is remarkably stable and falls within a very narrow zone known as the habitable zone, or the Goldilocks zone, not too hot, not too cold, but just right for liquid water to exist. This orbital stability is a gift of gravity. The Sun's gravitational pull keeps us in this stable orbit, and the arrangement of the other planets, particularly the giant Jupiter, helps to shield the inner solar system from too many comet impacts that could cause catastrophic climate shifts. If Earth's orbit were more elliptical, like that of Mercury, the temperature swings between its closest and farthest approach to the Sun would be extreme, making it incredibly difficult for a stable climate to develop. A slightly different gravitational dance in the early solar system could have easily placed us on a different path, one where even a supercharged greenhouse effect would have been insufficient to prevent a global ice age or a runaway greenhouse effect like the one that scorched Venus. The faint young sun paradox, therefore, is more than just a question about Earth's ancient atmosphere. It is a powerful reminder of the incredible series of coincidences and delicate balances that allow a world to be habitable. It highlights that our existence is predicated on a chain of events involving not just the right chemistry, but also the right physics, governed by the precise and unwavering force of gravity. Our planet is a testament to a narrow window of opportunity, a specific stellar luminosity, a specific planetary mass, and a specific orbital distance, all held in a stable equilibrium by gravity for billions of years. This concept of fine-tuning, of a universe whose fundamental constants and forces appear to be perfectly calibrated to allow for complexity and life, does not stop at the edge of our solar system. It extends to the cosmos as a whole, leading us to the final and perhaps greatest gravitational wonder of all. And so we arrive at the final and perhaps most profound mystery on our list, a problem so staggering in its implications that it has been called the worst theoretical prediction in the entire history of science. This is the cosmological constant problem, and it strikes at the very heart of our understanding of reality, revealing a chasm between our two most successful theories so vast that it dwarfs all other discrepancies. The puzzle begins with a simple, seemingly innocent question. What is the energy of empty space? According to the well-established principles of quantum field theory, the vacuum is not a true nothingness. It is a seething, bubbling foam of virtual particles, pairs of matter and antimatter that spontaneously pop into and out of existence for fleeting moments. This quantum jitter is not just a theoretical curiosity, it has measurable effects in the lab, and when physicists calculate the total energy density that this frantic activity should contribute to every cubic centimeter of the universe, they arrive at a number. It is an enormous number, one that represents a tremendous amount of latent energy inherent to the fabric of spacetime itself. This is where Albert Einstein makes a triumphant, if posthumous, return to our story. You will recall that he introduced the cosmological constant, denoted by the Greek letter lambda, as a fudge factor to keep his static universe model from collapsing. After Hubble discovered the expansion, Einstein discarded it, but with the shocking discovery of dark energy and the accelerating universe, lambda was resurrected. The energy of the vacuum, it turns out, acts exactly like a cosmological constant, producing a repulsive gravitational effect. So we can now measure the strength of this dark energy by observing the cosmic expansion. Astronomers have done this with incredible precision, using supernova, the cosmic microwave background, and large-scale structure. The observed value of the cosmological constant is a very small, but definitely not zero, positive number. It is this tiny nudge that is gently pushing the galaxies apart. Now, here is the problem that defies all reason. When you place the theoretical prediction from quantum field theory next to the observed measurement from cosmology, they do not simply disagree. They are catastrophically, unimaginably different. The predicted value is about 10 to the power of 120 times larger than the observed value. To try to comprehend the scale of this error, consider that the number of atoms in the entire observable universe is estimated to be about 10 to the power of 80. This discrepancy is a number so vast that it is greater than the number of atoms in the universe multiplied by itself. It is not that our prediction is off by a factor of 2 or 10 or even a million. It is wrong by a factor that is essentially meaningless in any practical sense. If this were a financial forecast, it would be like predicting your bank account balance is a single penny, only to open your statement and find a balance of more than $1 trillion. The error is so colossal that it cannot be a simple miscalculation. It points to a fundamental flaw in our understanding. Why is this such a profound crisis? Because it reveals a breathtaking lack of understanding of how gravity talks to the quantum world. General relativity, which describes gravity as the curvature of spacetime, tells us that all forms of energy should contribute to this curvature. The vacuum energy predicted by quantum field theory is a form of energy, and a stupendously large one at that. Therefore, according to Einstein's equations, this vacuum energy should curve spacetime with such ferocity that the universe would have ripped itself apart in the first instant of its existence. The fact that we observe a universe that is 13.8 billion years old, with galaxies, stars, planets, and us, means that the actual curvature caused by the vacuum is almost exactly zero. But not quite zero. It is a tiny positive value that only began to dominate the universe's evolution billions of years after the Big Bang. Somehow, the incredibly large positive energy of the quantum vacuum and an equally large, but negative, something else must be cancelling each other out to an accuracy of 1 part in 10 to the 120, leaving behind the faintest whisper of a positive remainder that we measure as dark energy. This degree of fine-tuning is so exquisitely precise that it seems absurd. It would be the most miraculous coincidence in the history of the cosmos, a cosmic accident of unimaginable unlikelihood. This is why the cosmological constant problem is considered the ultimate gravitational wonder. It is not just another puzzle, it is a screaming alarm bell that our current theories are fundamentally incomplete. The solution will almost certainly require a theory of quantum gravity, a framework that successfully marries the probabilistic, granular world of quantum mechanics with the smooth, geometric landscape of general relativity. Candidates like string theory or loop quantum gravity attempt to do this, but so far, none have produced a clear, testable explanation for why the vacuum energy is so small. Some physicists speculate that the answer might lie in the multiverse. In this controversial idea, our universe is just one bubble in a vast cosmic froth of universes, each with different physical constants and values for the cosmological constant. We find ourselves in a universe with an exceptionally small lambda simply because in a universe with any larger value, galaxies could never have formed and life could never have arisen. This anthropic explanation is deeply unsatisfying to many, as it replaces a mechanistic explanation with a statistical one, but it highlights the desperate need for a deeper theory. The cosmological constant is more than a number. It is the dial that sets the ultimate fate of everything. A value only slightly larger would have led to a cosmic expansion so rapid that no structures could ever have formed. A value slightly more negative would have caused the universe to recollapse almost immediately. The fact that we exist to ponder this question is tied to this incredibly precise and unexplained fine-tuning. It is the final and greatest gravitational mystery because it encompasses all the others. It involves the nature of dark energy, the behavior of the quantum vacuum, the large-scale structure of the cosmos, and the fundamental laws that govern reality from the smallest scales to the largest. Unraveling this problem will not just solve a technical issue in theoretical physics. It will reveal why our universe has the character it does and what its final destiny will be. It is the ultimate question written in the language of gravity, a question we are only just beginning to learn how to ask. From the anomalous slowing of our Pioneer probes at the edge of the solar system to the inexplicable kick given to spacecraft during a planetary flyby, from the ghostly pull of the Great Attractor to the repulsive push of dark energy accelerating the entire cosmos, these 30 gravitational wonders have taken us on a tour of a universe that is far stranger, more complex, and more magnificent than we could ever have conceived from our small world. We have stood at the precipice of black holes where information itself may vanish, marveled at the perfect rings of light carved by gravity's lens, and traced the invisible filaments of the cosmic web that binds everything together. Each of these phenomena is more than just a puzzle waiting for a solution. It is a luminous guidepost, a sign etched into the fabric of reality that points toward a deeper, more complete theory of physics waiting to be discovered. They remind us with humbling clarity that our current understanding, for all its power and precision, is merely provisional. The elegant equations of Newton and Einstein are not wrong, but they are incomplete, like a beautiful map that accurately charts the continents but leaves vast, unexplored oceans marked only with the phrase, "Here be dragons." The most profound realization from this journey is that the force we experience every time we drop a cup or stumble on a step is the very same force that sculpts the largest structures in the cosmos and dictates the ultimate fate of everything. Gravity is the great connector, a single thread woven through the quantum realm, our daily lives, and the expanse of the universe. It is the universe's great architect and its ultimate mystery. The journey to understand it is far from over. In many ways, it has only just begun. With every anomaly resolved, new and deeper questions emerge. The detection of gravitational waves has opened a new window onto the universe, while the persistent tensions in our measurements and the glaring theoretical problems like the cosmological constant demand a revolution in our thinking. The next great breakthrough may come from a deeper stare into the cosmic microwave background, a new signal from a pulsar timing array, or an unexpected result in a particle accelerator that finally reveals the nature of dark matter. What do you think is the most baffling of these gravitational mysteries? Is it the sheer dominance of dark energy, a force we cannot explain, the ghostly presence of dark matter which shapes galaxies yet remains forever hidden? Or perhaps it's the paradoxical nature of black holes, where our two best theories of reality clash in a fundamental way. Share your thoughts in the comments below. We'd love to hear which wonder captured your imagination the most. If this journey into the cosmic unknown has sparked your curiosity, don't forget to subscribe and hit the notification bell so you won't miss our next exploration. The universe is filled with mysteries, and together we can continue to uncover its deepest secrets. Thank you for watching.